Okay, so so a great pleasure to have Nima here again, and he'll give his third lecture on scattering amplitudes and clusterhedron in kinematic space.
All right, guys. Okay. Well, I'm delighted to be able to do this again. Thanks for having me back, so I can finish what I wanted to talk about before. So I'm going to be talking about a sort of continuation of things that we're talking about before. The things in today's lecture are sort of largely from a collaboration in the past year or two with Song, Thomas Lamb, Hugh Thomas, Mark Spradlin on the n=4 side of things, which I probably won't have the time to get to, Julia Salvatore, Hadley Frost, Pierre-Guy Plamondon, and Yuntao Bai and Gongwan Huang, and specifically the story about clusterhedra beyond one loop, sort of heading towards all loops and all orders in 1/n, is based on work in progress with Giulio, Hadley, Hugh, and Pierre-Guy. Hugh and Pierre-Guy are mathematicians. Giulio and Hadley are young theorists. Okay, so here's just a plan for what we're going to be talking about today. There are sort of three parts. First, I want to go back to that very simple picture of kinematic space and this kind of dynamics in kinematic space, looking at the wave equation and so on. That very sort of simple, intuitive picture in kinematic space, and basically push it as far as we can go. And that's going to allow us to talk without any sort of heavy, particularly heavy mathematical machinery about a large set of interesting objects that are, of course, very closely connected to these to the ideas of cluster algebras and their associated polytopes and so on. But for the first part of the, but for part one, you don't need to know any of that. And at a few moments, some very non-trivial claims are going to be made. But you can, in principle, go check those claims easily. They're sort of remarkable algebraic claims. But anyway, so the first part is sort of is self-contained, and we're going to be talking about first talking about this picture of the isosahedron that we just saw in kinematic space from yet another natural physical point of view, involving a natural notion of time evolution in our kinematic space. That will extend to, we will abstract away that notion of time evolution, and that will let us generalize all these things to a bigger set of objects. And in this way, we will discover, following our nose, this fascinating set of objects that are known as finite type cluster algebra polytopes. I will also talk about what you can call binary geometries associated with these cluster polytopes. I'll tell you what that means. They're the sort of most rigid possible geometric realization of the sort of pattern of compatibility, the generalization of what the poles are that go together. And we'll see that that notion also generalizes all of these finite type cluster polytopes, and that this notion is yet another very natural connection to strings. So the notion of a binary geometry applied to this particular case of the isosahedron is actually a different description of the worldsheet, a gauge invariant description of the worldsheet, but exactly the same idea is applied to the other cases that don't have any obvious connection to a worldsheet, but where a lot of the magical properties that we expect of, in fact, all the magical properties that we know of sort of tree-level open and closed string amplitudes sort of port to these more general objects. So that'll be what we talked about in part one, and that will also sort of set up a motivation. We'll begin seeing some of the clustery notions of mutation and quivers and things like that. Then I'll start with part two with kind of first an overview of why these clustery ideas are these ideas of cluster algebras are going to be relevant and interesting. Just sort of an overview of the sort of big picture of what we're going to be trying to do. But most of part two will be really a crash course on cluster algebras. So if you are curious about this subject, I'm going to tell you everything you need to know to actually be able to play with it. So this is a vast mathematical subject. I'm not going to be able to cover all of it. nor even prove too many things, but I'm going to define everything that needs defining and show you in practice how you do calculations. Okay, so what? So that will hopefully, to any of you who are curious about this stuff, that will hopefully remove a barrier to actually playing with it. I'm going to try to condense what you need, to know to sort of jump into thinking about these things about cluster algebras in part 2, and then finally in part 3, we will take up the question of generalizing all of these ideas that we've been talking about to all loop orders and all orders in the 1/n expansion for the scattering amplitudes in this bi-adjoint theory. And as we'll see, and as I mentioned before, this subject is really about, if you were thinking that you were summing over Feynman diagrams, and we normally talk about the genus or the 1/n expansion for Feynman diagrams, here we are summing over the jewels of those diagrams. And so, associated with that is a certain cluster algebra structure for Riemann surfaces with punctures. So we're going to try to understand that cluster algebra structure. I mean, it's a famous and well-studied cluster algebra structure, but it has a number of novelties and mysteries associated with it that naively obstruct constructing the analog of these polytopes, and that allow us to connect to the physics of scattering amplitudes. And we'll see that there's in fact something sitting there in the structure of these punctured surfaces that actually tells you exactly how to solve the problem, and give us these notions of clusterhedra. And I'll tell you what we know about them so far and where we're going. Okay, so that's the plan. So let's begin. So this is just a very quick summary of the story that we got to last time. If you remember, we were thinking about finding a question to ask in kinematic space for this bi-adjoint theory, and if you recall, the variables for this bi-adjoint theory are these xij, where we imagine putting the momenta end to end to make a closed polygon. So this xij was pi plus dot dot pj minus 1 squared. So those are our kinematic variables. And the whole story began just by putting the kinematical variables down on a piece of paper. Recalling here, by the way, that xii plus 1 is equal to 0. So that's this null side of the null side of this momentum polygon. So here we just drew them end to end on a piece of paper, and we note that there are two natural boundaries where xii plus 1 is equal to 0. And so all of the kinematic variables naturally lie in this strip that we defined. We notice that there's an interesting sort of causal structure in this kinematic space from this basic fact that chords that are incompatible in the polygon correspond to those chords are past and future corners of a causal diamond that fits inside this space. So that was an early hint that we should just think about some kind of dynamical question in this kinematic space where we think about this variable as time and this variable as space, so the way I've drawn. Okay, so we also mentioned that in order to cover all of the variables once and only once, so we would have x24, but x24 is the same as x42. So we don't want to cover both of them. So covering all the variables once and only once corresponds to taking a certain chunk out of the space-time. There are many ways of taking this this connected chunk out of this kinematic space, and I've drawn two of them. And last time we spent a lot of time talking about this right triangle example, just because it's the simplest to draw. But everything that we say is equally applicable to the other case. Okay, and then the dynamical question that we asked was about the wave equation in kinematic space-time. We imagined solving the wave equation in this kinematic space-time. We could either think about solving the continuum wave equation and then sampling it at discrete points, or just solving a discrete version of the wave equation. In both cases, a sort of key point is this Gauss's law for 1 + 1 dimensions, which is kind of the integral form of the wave equation. And not only were we looking at a wave equation, we wanted to have a wave equation with the boundary conditions that we talked about already, where x was equal to 0 on these boundaries, but we asked for the solution to stay positive in the interior of this right triangle. And that positivity was the origin of all of the origin of all the magic. So in fact, if we just ask for the solution to remain positive inside, and we sample at a finite number of points, let's say on this pass boundary of this kinematic spacetime. If you recall, if we just specify the values of x on this pass boundary, we fully determine the values of x's in the interior. So we can just sort of sample them at a finite number of points if we like. And if we shoot the light rays into the kinematic space and form this natural grid, this null grid, then just asking for all of these points on the inside, 2, 4, 2, 5, 2, 6, all of these points, all these 6 points together with the 3 points that we have on the boundary, 1, 3, 1, 4, and 1, 5, asking them all to be positive, of course, forces you to be in the upper orthant for 1, 3, 1, 4, and 1, 5, but there are 6 more variables, and asking those 6 variables to be positive cuts out 6 more sort of facets out of this orthant, and the shape that you end up getting is exactly the icosahedron and exactly this ABHY realization of the icosahedron. And we explained where that came from, sort of more conceptually, that this comes from the fact that this picture of the wave equation in the kinematic space makes it obvious that we have the sort of space of all the x's on this boundary. This is obviously polytopic because the space of x's on one boundary is the allowed x's are clearly cut out by a bunch of linear equations, so it's obviously polytopic. But it also factorizes, obviously, and we gave this sort of simple argument for why when you go to the boundary of this space of allowed x's, so the space we care about is space of allowed x's, let's say on this pass boundary. If we move these variables on the path boundary around so that at some point in the interior we set x star to 0, which is going to the limit or the boundary of the space that we're allowing, then we argued that what you get is actually the direct product of 2 smaller geometries of exactly the same sort. So that's why we accomplished what we wanted, which is to find a realization, something that made it obvious that we had a polytope that factorizes on its boundaries to lower polytopes. So that was the whole point. As I sort of emphasized in the introductory part last time, the picture of Feynman diagrams in the string worldsheet makes factorization obvious, but it does not at all make the fact that there's this polytopal structure to the boundaries obvious. That there's a polytopal structure of the sort of allowed set of compatible poles obvious, nor does it make obvious that the scattering form is projectively invariant. And all of those things are now made obvious by this picture, because we have something that's obviously polytopal, it factorizes on its boundaries, and as we using the sort of general philosophy that we talked about earlier, the scattering amplitude is actually a form. It's a differential form that's defined on this kinematic space. It's defined everywhere in the kinematic space, but it's fully fixed by the requirement that when we pull it back to the solution of the wave equation, this positive solution of the wave equation, we get the canonical form of the icosahedron. And this makes the projective invariance manifest. And it also, in this particular realization, it also ends up being true, slightly non-trivially, that when we pull back to this subspace, we get this canonical form for the icosahedron that, in fact, after we factor out the overall volume form on the subspace, what we're left with is literally the amplitude. So all the signs in these projective forms go away, and we get the sum over everything. All right, so that's just a summary of what we discussed last time. So now I want to, and again, Feynman diagrams are one particular triangulation of the icosahedron. They have this feature that term by term, they have a spurious pole at infinity that breaks the projective invariance. Only the sum over all of them preserves projective invariance. But there are many other triangulations that manifest projective invariance. They're vastly more efficient than Feynman diagrams for calculating these amplitudes. And as we discussed, there's a method of stringy canonical forms that you can apply to compute the canonical form of any old polytope coming along with an alpha prime. But there's a natural fact about this icosahedron, which is that it's naturally represented as a Minkowski sum of simpler pieces. And that representation, the stringy canonical form associated with that rigid representation is exactly the Jacobi-Nielsen formula. So it gives you the actual string amplitude of finite alpha prime. We'll see another related, but another somewhat more invariant picture for the connection to the worldsheet and to strings a little later this lecture. All right, so that's a summary of everything that we talked about last time. Now, so let's start with the new things. Now I want to go back and talk again about solving the wave equation. But instead of doing it in this global way, where we use Gauss's law to solve for all the points inside, I want to do it in yet another way that's natural from a physical point of view, which is via time evolution. So what do I mean by time evolution? Well, again, if you imagine this is kind of a discretized grid for solving the wave equation, and remember we have this zero. Again, we have these boundary conditions on the end here. Well, let's say I give you the initial conditions at these points, like 1, 2, 3, and you want to you want to use time evolution to push this surface forward. Well, what that means in this context is that remember the discrete wave equation is just the smallest Gauss's law. So the Gauss's law associated with the tiniest diamonds, or sometimes we call them meshes, like that one. Okay, so so you have to look here and see which mesh can you use that, given this information that I have on the slice, allows me to solve for a new variable. That's what time evolution means, right? I want to be able to solve for one new variable at a time and then evolve as I'm moving forward. Okay, so what does that mean in this context? Well, which mesh can I use? Obviously, I can't use someone up there. I can't use someone far away. So I can't use this guy. I can't use this guy either, though, right? Why not? Because that Gauss's law would tell me that, like, this thing that I don't know plus 3 minus this thing that I know that I don't know minus 0 is equal to 0. So it involves 2 unknowns. Okay, so I can't use that mesh either. The only mesh that I can use is actually this one here. If I use that one there, then that mesh tells me if this new point up there, I'll call it 4. If I call this point up there 4, then I learn that x4 plus x1 minus x2, and this is 0 here, so minus 0 is equal to some mesh there. I don't know, maybe I'll call it C1 to remind me that it was associated with 1. Okay, so you see, so if I do that, I can solve for this point 4. So now I know the point 4. Okay, and I can move up. I can move on in that way and solve for everything else in the interior. And here I've denoted it. So we start with 1, 2, 3. Then I can solve for 4. Then I can solve for 5. Then I can solve for 6. Now I have a few choices for how I can proceed, but for example, I can now solve for 7, and then 8, and finally 9. So in this way, we have like a picture of this sort of Cauchy surface that's gradually being pushed upward into as we evolve in time. Okay, so that's a very natural physical picture. Now we're going to abstract it away a little bit. Okay, so we're gonna abstract it in the following way. Associated with any one of these quote unquote Cauchy surfaces, I'm going to associate with every one of these Cauchy surfaces a certain quiver. Okay, so a quiver is nothing but a graph with some nodes and some edges, but the edges are directed. So the arrows they're arrows. The arrows have a direction. And so, for instance, with this initial Cauchy surface, 1, 2, 3, I'm going to associate this quiver x1, x2, x3 with an arrow going from x1 into x2 and from x2 into x3. And the general rule is that for every one of these, for every surface, the quiver is going to have an arrow from A into B if A is in the past of B. Okay, so that is the rule. So that's clearly satisfied here. So let's go to the next one. In the next one, 2 is in the past of 4 and 2 is in the past of 3. So we have this quiver. So with the arrow going out from 2 into 4 and out from 2 into 3, just as I've drawn. Okay, and so on. So all right. So so you see that the picture of time evolution in this Cauchy surfaces can be represented in the following very simple way. I start with my initial quiver, and then I take any node which is a source. So it has an arrow going out. So here I have something, this is x1, and then I make a new quiver. And the new quiver is simply, I reverse the sign, I reverse the orientation of the arrow going into that node. And I also replace the variable associated with it. So here I have x1, and so x1 is the source. So I'm going to change x1 to the next variable x4. I'm going to reverse the arrow going into it. Okay, so this is my next quiver, and now x2 is a source. So notice in any tree quiver, it's guaranteed there's always at least somebody who is a source. That's not true if you have a loop, but if you have a quiver, which is a tree, or more generally so-called acyclic, then there's always somebody who is a source. And in fact, all that's going to change, we're only going to change the orientation of the arrows as we go along. So now 2 is a source. So from here, I can mutate. And this operation of flipping the arrows, I'm going to call mutation. Both flipping the arrows and making a new variable we'll call mutation. It's a special case of the mutation we'll see associated with general cluster algebra. So when we go from x2 to x5, now I reverse the sign of the arrows, and now I have x4, x5, x3. Okay, and again, indeed, that precisely corresponds to this new Cauchy surface up there. And so on. See, now I have a choice. I could either mutate at x4 or I could mutate at x3. And it doesn't matter which one I do. So here I chose to mutate it at x3 to make x6 and so on. Okay, so we can follow this process, and that's a slightly more abstract way of talking about this notion of time evolution. This process of mutating on sources we sometimes call a walk. Okay, so we start from a source and then we just mutate on any source as we go. Also, we can also say what the formula is for the new variable. So if I mutate at some vertex v, my new variable xv prime is determined is by the following formula. This is just our Gauss's law condition. xv plus xv prime is minus the sum of all of the remember, V is a source, so all the arrows are going out of it. So I just sum over everyone that it touches, the x's of everyone that it touches, so all the w's, such that V goes into w of xw, and that's equal to a sort of mesh constant associated with each one of these meshes as I mutate, which I'm just going to call CV. Okay, so this is a small abstraction away of the simple rules that we've seen here, phrased in the language of mutating a quiver and writing down these simple relations to determine the old variables in terms of the new one. Are there any questions so far?
Nima, hi, we cannot see your face. Is it possible to somehow?
Oh, I'm sorry. You can't see. Oh. Huh, that's surprising. Oh, sorry. I think there are 2 screens.
Yeah. So is it possible to somehow, I don't know, otherwise it's okay if it's not possible to.
I mean, let's see.
Now we can see. Now we can see.
Right, but I thought my second screen is, I thought, I thought the whole point was that my second, hold on. In fact, let me try something. So, I actually shut one of them off now. Can you see me in the second screen or not?
Yes, we can always see you.
Yeah.
Okay, fine.
Thanks.
Very good. Very good. Sorry about that. Okay. So now there's only one thing that so we've almost entirely abstracted away this picture of time evolution in terms of a rule on this quiver, but not quite, because in this picture, so in the upper picture, it's clear when we stop. We stop when we get to the end, right? And we can't. But purely from playing this game on the quiver, what tells me I have to stop? For example, at this last step, why don't I keep mutating on x6 to make some x10, and I just keep on going forever? Okay, so there has to be something a little bit more that tells me purely at the level of this quiver where I stop. And this is the answer. So let's just see what happens in this slightly simpler example. This slightly simpler example would correspond to the case of 5-point scattering. So it would be this picture. Okay, so we'd begin with, let's say, 1 and 2 here, and then in the next step we would solve for 3, and in the next step we'd solve for 4, and in the next step we'd solve for 5. So the sort of question again is why we stop there and not keep going. But let's just see what happens as we go. So for instance, in this first step, we would solve that x3 is equal to, let's just write down what the formula is. So we have x3 plus x1 minus x2, right? So that's the arrow going out 2 is equal to, let's say, c1. All right, good. So that lets us solve for x3 is equal to c1 plus x2 minus x1. Okay. Now, remember that we're interested in keeping all these variables positive. So to begin with, before we did anything, we knew that we had to be in this upper orthant here, in this upper quadrant for x1 and x2, right? We knew we had to be in this upper quadrant x1 and x2, but already at this first step, now that we've solved for x3, we have another constraint. Having x3 be positive forces another constraint on x2 minus x1 is greater than or equal to negative c1. And so in addition to these constraints, we also have this one, okay? Right, so now instead of just being in the upper orthant, we have to be, beforehand we have to be in this region. Now we're learning that we got some constraint. We have to be in on this one, okay? And I can also record what I know about the sort of normals of the faces of the walls that I'm building as I go along. So to begin with, I just have my walls in the sort of one in the sort of the normal point in the 2 direction and in the 1 direction. Let me draw it a little different color, in the 2 direction and the 1 direction. So I've summarized them here. Those are the normals. In the next step, now I have another normal that points in this direction. So that's a normal associated with x3, and so now we have this picture. Okay. And now you just keep going. So at the step after that, you have x4, and you find that and now adding x4 forces this wall in the problem. So now you have to live in here, okay? And finally, x5 also adds this final wall, and now you're done. Now you've built a finite shape. Up to this point, it was infinite. Up to this point, the shape was infinite. But finally, when I got to x5, I closed it up into a finite shape. And slightly more algebraically, if you like, if I don't get to draw the picture, this is equivalent to the following: that as I go, I can solve for every new variable, and express it as a linear combination of the ones that I started with, okay? And that's what these vectors are. So this vector here, this vector for x3, which is x1 minus x2, okay? So, this vector for x3 is x2 minus x1. So that's, here it is, x2 minus x1. Let's ignore this constant piece for a second. These little two-dimensional vectors are just recording what the linear combination is of x1 and x2 that x3 is written as. So here, so this is x2 minus x1 is this vector. So this guy would be negative x1, and this guy would be negative x2. Okay, so that's what you get up to these constants. If you like, it's what you get from just the homogeneous wave equation with no sources. The point is that as you mutate, as you go along, there's a condition on when you can mutate, where you can mutate, and the condition is simply that every new vector that you make has to be outside the region spanned, positively spanned by the old ones. So it's kind of cool. There's a sort of a notion, vaguely a notion of entropy that constantly has to be increasing as you do this time evolution. Every new variable that you make has got to be outside the convex hull of the old one. And so you can mutate any way you can until, so long as that's true. The moment that becomes impossible, you have to stop. And so you see that becomes impossible at this last stage because finally I make this variable x5. Now, so beforehand, when I start with, the only things that are in the positive combination of 1 and 2 would be this region. 3 was outside that region, so adding 3, I've expanded my region. 4 is outside again, so I further expand the region. But when I finally add 5, if I ask what's a positive linear combination of all 5 of these guys, well, now with 5 we've covered everything. And so any 6th vector is necessarily going to be inside one of these regions. It can be written as a positive linear combination of some of the old guys, okay? So that is the rule, is that there's a sort of notion of some quantity that has to monotonically increase as you do this quote unquote time evolution. And that quantity is a kind of a measure of how complicated this set of vectors is that you're getting, and has to just keep getting bigger and bigger and bigger. Alternately, geometrically, the first way we talked about it, you begin just with this upper orthant, and then every new equation that you get cuts out a facet of this polytope you're eventually going to get. So you cut out a facet, you cut out another one, you cut out another one, until you cut everything out, and it's a finite polytope, and then you have to stop. Okay? So these are two equivalent ways of, there are two equivalent ways of talking about it. Actually, this last way that I said is very slightly imprecise. So really the most precise statement is the first one that I made, that you have to make that the normals to all of these, have to, you have to stop once the, each one of the, you have to stop once the set of all the vectors that you get cover all directions in space, so that you can positively expand any vector as a linear combination of the vectors that the positive linear combination of the vectors that you've seen already. Okay, so any questions about this? Okay, so if not, what we can now do is abstract away this notion of time evolution. Okay, so we started with this familiar picture of a null grid and something that looks sort of familiarly like time evolution, but now we're going to generalize this as something that we can associate with any quiver. I'm drawing quivers that are just trees here. So if you have any quiver which is a tree, then and you orient the arrows any way you like, then this is guaranteed to make it possible to at least define the rules. And the rules are, you take any, you start with any source, you mutate on the source by reversing the arrows, you write down this equation to determine a new variable in terms of the old one, and you keep going. And you keep going until you're forced to stop. And forced to stop is so you just keep going, so that at any point you check to see whether the new variable that you solve for, which is associated with a vector, which where you expand it in terms of the basis of the original ones, you just want that new vector to always be outside the cone of all the previous ones. Okay, so now that vector, so in this way, we're going to be assigning a vector to every variable that we see. The vector, again, is simply expanding that variable in terms of a linear combination of the initial set. That vector is called a G vector, and we'll talk more about it. It'll play an important role in a lot of our later. But anyway, so here we've just seen it following our nose in this way. This is just for cluster aficionados. What I've described here is something well known in cluster theory and quiver representation theory, and is known as the Auslander-Wright-Watt. But if you don't know that, never mind. Okay, now I told you before that I was going to declare some remarkable things without proving them, and here's the first declaration. You can play this game for any tree quiver. You can define it for any tree quiver, but you can ask: is it always the case that it eventually stops? It is always the case that if you build this polytope, eventually it closes up into a finite polytope, or eventually the set of normal vectors. Notice that again, all of these G vectors that we defined before are equivalently the normal vectors to the facets of this polytope, as we saw in our previous example. Do the normal vectors eventually, these ersatz normal vectors of the polytope eventually cover all of space? And the amazing thing is the answer is almost always no. If you take a generic quiver, it'll go on forever. It'll go on forever, and you won't get a polytope that closes up. Okay? In fact, it's very, very special when the polytope does close up. And here is the incredible answer. Now, here I've given a sketch of one way of understanding it that relates to the Coxeter groups. There's a few other ways of thinking about it, but let me just tell you the final answer. The final answer is that you get a finite polytope if and only if the quiver that you started with is actually an orientation of a Dynkin diagram. Okay, so now this is just a totally unobvious fact that Dynkin diagrams have anything to do with this. Dynkin diagrams have shown up a few times in the 20th century in different guises, and this guise is not at all closely related in any obvious way to the classification of Lie groups, at least to begin with. So do not, these Dynkin diagrams have nothing to do with the Lie algebra of the underlying bi-adjoint phi cube theory, whatever that group is for the color. They're utterly unrelated to each other. Okay, so but this is just another remarkable occurrence of the Dynkin classification. But anyway, that is the rule: is that if you take the orientation, so if you take a Dynkin diagram, so here are all the summary of the Dynkin diagrams. We have the classical types for types A, B, C, D, and type A is just a chain. And when I say oriented any way I want, I mean put arrows on this chain any way you like. Okay, so when you do that, you get some starting quiver, and then follow the rules, and you'll find that it always closes. And in fact, the polytopes that you get from orienting AN are exactly the ordinary associahedra. But if we follow the rules that we get the ABHY associahedra for this case. But we can do exactly the same thing starting from DN. Okay, so I can put any orientation there that I like, and that also gives you a different polytope. You can call it the DN cluster polytope. I haven't justified the word cluster yet, but anyway, we're going to be using that language. So it's a DN cluster polytope. As we'll see in a moment, I'll try to give some intuition for why it's true. This DN cluster polytope actually, the associated canonical form actually gives us all the one loop amplitudes in the integrand for the one loop amplitudes in this bi-adjoint phi cube theory. Now we have these other We have other classical Dynkin diagrams, Bn and Cn. Here there are these double arrows, so we have to figure out what these double arrows mean. And for the double arrows, there's actually a small extension of this rule. Okay, the small extension for this rule of mutating on the sources is that we can allow some integer nw in front of xw. Okay, so that's just a small extension. So it's still 1 plus 1 here, but we allow some small. We extend the rules by allowing some integers out in front. If you extend those rules, then you only get a few more things, but the most general set of things that you can get, which are finite, where these rules terminate in the way that I defined, gives you all of the Dynkin diagrams, not just the simply laced ones. So so I can have like E6, for example, and that's a fine example. That's simply laced. I can orient this any way I like, and if I do that, I'll get some finite. I'll get some finite 6-dimensional polytope. But the other classical families involve these double lines, and so they involve some integers, some 2s that are there in that formula for time evolution. Okay, so that is the claim, is that once you abstract away time evolution as a rule for mutating on sources in a quiver with this quasi-entropic rule for where to evolve and when to stop, amazingly you find only a finite. You find that all the ones that give you finite polytopes are simply orienting are quivers that are given by orientations of Dynkin diagrams. And in fact, all of these guys, all these classical types that have an n associated with them, which is what you would naively need to be related to a scattering amplitude, all of them are related to amplitudes. As I told you, an is tree level, dn is 1 loop. Bn and Cn end up also being 1 loop, but only a subset of 1 loop diagrams where you omit a tadpole. We don't know the direct physical interpretation for the exceptional finite ones yet. Okay, so and you can now ask what happens at sort of 2 loops and beyond, and that's what we'll talk about in more detail. They're no longer associated with Dynkin diagrams, but there are certain in the first extensions you get affine extensions of Dynkin diagrams. In general, they're not, but we get nonetheless that there are quivers associated with them, and this is a story of the cluster algebra of punctured surfaces that we'll come back to in the last of the topics today. Okay, so all right, so now let me give you a little bit of intuition for why. Let's skip. I'll come back to it in a second. So how do we see what is this? How do we see factorization at the level of these quivers? So this is a very cool thing that really is a consequence of everything that I told you, but I'm just going to declare it. I hope it sounds plausible, but it's a beautiful and not non-trivial fact. So I told you that with every Dynkin diagram, we get one of these polytopes, and it's a natural question to ask what the facets of the polytope look like. So when I go to a one-dimensional codimension 1, when I go to a face of the polytope, we already saw for the case of the isosahedron that I don't get some random polytope there. I get the direct product of 2 lower polytopes. So what happens in general for these extended polytopes that we get associated with any Dynkin diagram? And the answer is all the polytopes that you ever see on the boundaries. So the faces of these polytopes are other polytopes of the same type obtained by removing one node of the Dynkin diagram. Okay, so that seems quite reasonable. You want to go down one in dimension. The dimensionality of the polytope is just the number of nodes in the Dynkin diagram. So if you want to go down one in dimension and you're going to live within this world of objects, what else could you do other than remove one node? So let's see how it works. So let's do the example that we're familiar with already of AN. Okay, so as we just saw, the story with the right triangle of solving the wave equation of the right triangle region is just this quiver. Okay, but anyway, it doesn't matter. This is just showing that it's the AN quiver. So the orientation, any orientation works. So let's just draw it without orientation on the arrows. So if you have AN, then the claim is that the sort of boundary of what I get from the AN polytope is all the boundaries I can are just deleting some node. So let's say I delete this node. Well, what do I get? I'm just left with the product of two other ANs. And that's exactly correct. So we get that the boundary of AN, the boundary of a, actually let me call this D in order not to confuse it with the N of the particle scattering. So the boundary of AD is just equal to AD1 cross AD2, where D1 plus D2 is equal to D minus 1. But now let's remember that the amplitude for N particles is associated with, let me not put an equal sign, but is associated with the N minus 3 node. It's an N minus 3 dimensional space. And so this rule is the same as saying that the boundary of the singularities of the endpoint amplitude is Mn1 cross Mn2, where N1 plus N2 is equal to N plus 2. Okay, and that's exactly what we expect. That's exactly this picture. Of course, you know, I've seen it many times now, where on that a boundary corresponds to a factorization channel where I have these two extra particles. These two intermediate particles are the plus 2 that I see there. Okay, so that's the first sort of familiar example. Let's do another example. Let's now look at Dn. So first, let's look at it kind of abstractly. So if I have the boundary of D for dimension little d, then one way I can remove a node is to remove one of the ones in here. Okay, so then what I'll get is the product of a type D and a type A. Right, so I'm just going to get a chain on one side and a type D on the other side. Okay, so this is going to be a D D1 cross A D2, where D1 plus D2 equals little d minus 1. And at the level of the amplitude, this is some sort of this is a singularity of the amplitude of. So I'm claiming this is a one loop amplitude, and I'm now trying to give you a justification why it's a one loop amplitude. I want to identify all the kinds of factorizations that we expect at one loop and see that they're exactly the same as the boundaries we expect for this polytope. So one part of a factorization of a one loop amplitude is something that's a one loop on one side and then is a tree on the other side. Okay, so and that's exactly this kind of factorization. Okay? So in fact, we would see that for Mn, I would have an N1 and an N2 here, again with N1 plus N2 is equal to N plus 2. All right, so that's good. But there's another kind of a boundary that this Dynkin diagram has. So let's go back. Another kind of boundary that it has is to delete, say, one of these antennae. Okay, so now this gives me that the boundary of DD is equal to A, but with D minus 1. Just a single A with D minus 1. Now, what could this mean at the level of the amplitude? At the level of the amplitude, D, this is now, I should have said that Dn is n.1 loop, whereas An is n minus 3 point tree. So I didn't say this thing about the relation between the ends, and that's exactly going to be what makes that's the identification that's going to make things work out for what I'm just about to show you. So this tells us that the boundary of Mn at one loop, in other words, a pole of the one loop amplitude with 10 points should equal A of n plus 2. Sorry, the tree amplitude with n plus 2 particles. And what is this? Well, this is precisely correct. This is the sort of famous fact that if I look at a one loop amplitude, like let's say I look at this box diagram and many other diagrams that would contribute to the amplitude, but there is a pole where this internal propagator goes on shell. So let me look at this pole. Now the residue on that pole, I mean, if I put this thing on shell, this is exactly as if I just cut this open with two equal and opposite momenta here, but the rest of it is like a tree. Right, so there's some L here and some minus L. And so you see that this is the so-called forward limit. And we see that a pole of one loop should reveal, with n points, should reveal a tree with n plus 2. Okay, so it's exactly this thing of going from n to n plus 2, and from one loop to tree, and that's exactly what we saw in this kind of factorization. So if I summarize the story, we have for an that the boundary of an is an1 cross an2, and this reflects the fact that the level of the amplitude that we have the only kinds of singularities, single poles, are factorization, whereas for this Dynkin diagram, the boundary of Dn is Dn1 cross An2 for one, and then another one is An minus 1. Okay, so these are the kinds of boundaries we can have, and this reflects that the one loop amplitudes can factorize with a single particle going on shell in the middle with one loop on one side and tree on the other side, and also a tree amplitude with 2 extra particles. Okay, so that's at least some motivation why this Dn, why the polytope that we would make associated with the Dn should give us should give us something related to one loop amplitude. All right, maybe I will stop here and ask if there are any questions. Oh, sorry, maybe before I do that, let me just show you a picture. I flashed this briefly last time. In the language that we're talking about, if I start drawing Feynman diagrams at one loop, I would draw these, the Feynman diagram, and the jewel of the Feynman diagram is a triangulation of a polygon, but with a hole or a puncture in the middle. So if we look at this example at 4 points and I draw the box, the jewel of the box is this picture where there's this X in the middle, and I draw, this is now giving me a triangulation of the square, but with this little hole in the middle. And then, and we can talk about the various variables that we can see in this way. I'll be talking about this a little bit more generally when we get to the general clusterhedron story later. I just want to show you what this kinematic space looks like in this example. So this is the thing that's going to give us this dn polytope, which is supposed to give us the one loop amplitudes. And I just want you to, this is going to be a little impressionistic, but I want you to see how these things are related to each other. If you remember, when we drew this picture, we had our wave equation. Sorry, we had our kinematic space picture, and we could kind of see these quivers, right? So here is here is the first quiver, then we can see the sort of next quiver just by mutating, right? Just by solving one at a time and so on, right? So, and we have the exact analog of that in this picture. So this is another picture of a kinematical space-time where kind of at this end, there's a funny doubling. That doubling is associated with the antenna of the dn quiver. And so the precise analog of the previous picture is just this. So here is my dn, my initial dn quiver is, let me see if I can make it clear, is this guy, that guy, and these two. And so here is the initial quiver. And now everything in green here involves solving for a new variable in terms of the old one. So I can solve as I go. I can solve on starting from this green thing, starting from here. I can solve. So the fact that I have this guy connected to 1, 2, 1 connected to 1, 2, and connected to 2 means that I write down the formula 2 plus 1 minus 1, 2 minus 0 is equal to that to the green mesh constant. So that lets me solve for this variable 2. And similarly, starting from 2, so this was 1, starting from 1 tilde, I can do exactly the same thing and solve for 2 tilde up there. Okay, so that's how I solve for those variables. And then I simply go on and I solve for all of the all the rest of them. The amusing thing is, like, let's say at this step, if I want to solve for this guy, the formula is that 1, 2 plus 2, 3. But now notice that 1, 2 is actually connected to both 2 and 2 tilde. So in the formula for 1, 2 plus 2, 3, I would have x1, 2 plus x2, 3 minus x2 minus x2 tilde. Okay, both of them. So I would get the sum of I'd get the sum of both of them there. So these guys where they're the double arrows, well, it's exactly what you get. This picture is simply a way of combining together all the chain of mutations, starting from the original dn, starting from the original orientation, which was, for example, all these arrows going out like that, and just mutating one variable at a time by the rules. This picture is just combining all of the formulas for each mutation step together, so you see them all in one geometric picture of the kinematic space. In the kinematic space, now with this little extra decoration of having 2 variables at one end. And I will talk later about what these 2 variables are. These 2 variables are really associated with the fact that we have naively one kind of loop variable, but for good reasons, they end up having to be doubled up. So I will talk about that a little bit later. Here, I just wanted you to see that, as with the AN example, in the DN example, we can summarize all of both the mutations, the quivers, the mutations, and the equations, all in a picture of something that looks like a wave equation in the kinematic space. Now, this little extra decoration of having what looks like maybe a brain or some extra degrees of freedom living on one end of this kinematic space. Okay, but just so you see that there's some concrete polytopes associated with this. Just as before, we had that all the tree amplitudes could be drawn on, all the tree amplitudes can be drawn on the surface of, can be associated, all the Feynman diagrams can be associated with the vertices of some polytope. The same thing is true at one loop. So here's an example for the 3-point amplitude that all the 3-point diagrams, and interestingly, including these tadpole diagrams, including bubble diagrams, so you can't just throw things out that integrate to 0 or something like that. In this story, they're all there, they're all important, but they're all indeed vertices of these interesting cluster polytopes associated with these quivers. All right, maybe I'll take a break there and see if there are any questions.
Yeah, can I ask a question?
Yes.
So in the DN quiver, so there
Yes.
was a node that was connected to more than 2 nodes.
Mm-hmm.
What does it mean to, if am I allowed to remove that node?
Oh yeah, you can. Yes. So let me. So that's a great question. I forgot to say that. So that at first looks slightly confusing. Let me just say. So let's keep looking at all of them. So you're saying what happens when I remove this node? So that naively looks like something funny. It looks like I have a factorization into 3 pieces.
Right.
But in fact, this guy is just the this is D2 cross AN, and D2 just happens to be A1 cross A1. So this is the you know, the famous fact that SO4 is SU2 cross SU2. Okay, so this is still counted in the boundary where it looks like a D cross an A.
I see. Okay.
However, we can ask about the other guys. So, you know, just if we wanted to say what kind of connection could, for example, the E6 guy have? Well, in E6 there really is something now genuinely interesting. Whatever these objects are, if they have somehow connected to physics, we need to think about something which has a good reason to factorize into a part with 3 pieces. So if I remove this node, then this really genuinely factorizes into an A1 cross A2 cross A2. Okay, so whatever this E6 thing is, it needs to everything in physics factorizes in 2. So this has got to be something that sort of factorizes in 3 for a good reason. Did that answer your question?
Yes.
Okay, great.
Can I ask a question?
Yes.
Yeah, sorry, I missed the part about the wave equation. So for the loop, you said that the Gauss law constraint generalizes by adding a constant A in W. So does it mean that the wave equation also generalizes to some extent?
Yes. I mean, the whole story is exactly the same. I mean, what we did is abstract away the wave equation to this rule about the quivers, and that's it. I mean, so let me explain this picture a little more. You could really just begin. You could just begin with this quiver. So here's what I'm saying. Let's say we're doing D4. So D4 is supposed to be n equals 4 one loop. Okay, but I don't yet know that. I mean, later we'll identify how these variables are related to one loop amplitudes. But really, just abstractly, what you're doing, you start with 4 variables. I orient any way I like, and then I just mutate. I just follow the rules. So here, for example, I would maybe x1 is a source, so I would do this. So it gets some x5. So x5 plus x1 minus x2 is equal to c1. Let's say the first one. Okay, and now at 2, I would say now 2 is a little more interesting because I would say x2 plus x6. So 2 is now a source. So now I reverse all the arrows. I have x6, x5, x3, x4. So now I have x2 plus x6 minus x3 minus x4 minus x5 is equal to c2. So now there are 3 terms here because x2 now talks to 3 things, is attached to 3 things, and so on. I just keep going like this. And at every stage, now this is a four-dimensional space. So x5 is equal to x2 minus x1 plus c1. Let's never mind. So that vector that we're talking about would just be x2 minus x1, and x6 is x3 plus x4 plus x5 minus x2, okay, plus c2. So x5 would be this vector, 1, 2, 3, 4. x5 would be minus 1, 1, 0, 0. x6 would be 0, minus 1, 1, 1, 1. Sorry. Oh yeah, sorry. And now I have to. Sorry, I apologize. So this is what x6 is, but I have to. But x5 itself is x2 minus x1. So this is x3 plus x4 minus x1 plus some things with the constants there. So x6 would be minus 1, 0, 1, 1. So you see, as I go, I record what these vectors are, and then I just check. So here's x1, x2, x3, x4. I just check if the new vectors are outside the cone generated by all the previous ones. In this case, if you do that, you'll find that you can only take 12 steps. Okay, if you just do it on the computer, you just find you can only take 12 steps and you're done. You have a total of 16 variables, and you have a total of 16 variables, and you are done. And you get this finite polytope, and the claim is that that is a polytope which is whose canonical form gives you the one loop integrand. Now, purely abstractly, if you want to know how can you associate these variables with the variables associated with the amplitude, if you didn't know anything ahead of time, well, you'd actually discover it by looking at what its facets look like. And as you go, however you label them, you would discover which combinations of the variables come together at the vertices. And however you label them, you will find that that combination of variables is exactly these ones that I see in this picture. Okay, so I would really see that the combination of variables can be put together in a way that looks like all these one loop diagrams, even if I didn't know intelligently how to label them ahead of time. You can label them intelligently ahead of time, and that's what this sort of this simple kinematic space picture is suggesting for you. Okay, so if I label them all, so here's my initial quiver, and if I label the nodes 1, 1 tilde, and then this guy 1, 2, and 1, 3, and then all of these green meshes are exactly. Remember, I told you there are 12 steps. So where are the 12 steps? Well, I have to solve for all the new variables. All the new variables here I'm solving. So I see here 1, 2, 3, 4, 5. I see 6 meshes here. So those are associated with 6 steps, and each one of these is actually associated with 2 steps, because I can use this mesh to solve for 2 and for 2 tilde. Okay, so there's actually 2 equations associated with this mesh. So I have a total of 2 times 3 plus 6 equals 12 equations in total here. Okay, so this picture is summarizing all the 12 the steps that you can take in the time evolution picture associated with the DN quiver. And again, it's quite beautifully, except for this little decoration at the end. Again, all the equations just look like these mesh formulas. They look like x plus x minus x minus x minus x. That's our generalization of the wave equation.
Yeah, so this was one for DN, and similarly, will you have the same thing for BN and CN, which give rise to
that's right.
typos?
BN and CN have a very similar description.
Okay.
In fact, as is familiar even from what the Dynkin diagrams look like, it's most convenient to think about DN, and it's most convenient to think about them as kind of folding guys that we had before. For example, if I take DN and it's kind of like doing an orbifold. Okay, so if you take, so let me first describe the language of AN. So if you remember, for AN we have this sort of kinematical space that looked like the strip. And one thing that we did is we started off talking about the inside of this triangle. Well, we could do something more symmetrical, and something else, and talk about the inside of this square. Now here I've drawn the picture in the continuum. If you draw it in the discrete, you really have to take everything has got null lines here, so I have to take something that looks like that. Okay, but anyway, so I have to take the interior of a region that looks like that. But let me just draw it as a square. Okay, well, so this square has a reflection symmetry. So I can take this square and I can just demand that everything is symmetrical around flipping around that line. Okay, so if I take this realization of AN and then fold it just by literally identifying the variables on the two sides together, then I'll go from AN to CN. And actually you can see why, if you do that, in terms of the CN variables, my x plus x equations are going to have some factors of 2, because there are two variables that are now being identified. So what used to be x plus x prime equals, x1 plus x2, x1 and x2 become identified sometimes, and so I get a factor of 2x. Okay, so that's how I go from AN to CN. And similarly, I can go from DN to BN by identifying the I and I tilde variables. Okay, so there's a natural way of getting the other ones from A and D, but you could also just do them ab initio, just following the rules as I've described them, also for types B and C directly.
Okay,
Did that
thank you
answer your
very much.
question?
Yes, thank you.
Okay.
Nima, there's a question in the chat.
Yes. Let me see. Does a Dynkin node cutting argument work beyond finite type? Kind of, but the issue is what we mean work and what we're doing beyond finite type, because the whole problem is that there's no obvious polytope beyond finite type. So we first have to deal with that problem, and then we'll see what the boundaries look like. So we'll get there in the last part of our argument, in the last part of our discussion. All right, great. So there's one more topic. It deserves longer, but I'll just say a few things about it, which we're well positioned to see now, which is that all of these cluster polytopes are actually also associated with a beautiful notion of a binary geometry. And this notion of a binary geometry, when specialized to the case of AN, is essentially a different gauge invariant way of talking about the open string, actually open and closed string world sheets at tree level. What it means for the other cases is still not obvious. If it's related to so first there's a notion of a binary geometry that's associated with all of these cluster polytopes, which also gives us another way of talking about these stringy canonical forms associated with all of these cluster polytopes. In fact, I think an even more rigid and more invariant way of talking about what these stringy canonical forms are. So let me just give a sort of a lightning introduction to this set of ideas. One sort of theme that we've seen over and over again is that we have certain objects like triangulations of a polygon, where we have good and bad, compatible and incompatible variables. And what we've seen, what the zeroth order remarkable thing is that this pattern of compatibility going all the way down to like triangulations, which are maximal factorizations, if you like, or partial triangulations, which are partial factorizations. The pattern of compatibility is associated with a polytope, is associated with the icosahedron in this case. So for instance, if we do even the pentagon, where it just randomly it happens that the icosahedron is also a pentagon, then the fact that we have, so this diagram would be associated with one of the edges of the pentagon, right? And the fact that another one crosses it means that this diagram with the second edge would be some face, another face that doesn't touch the first one. So if I have two faces that are incompatible, then if I have two edges that are incompatible in my sort of kinematic polygon, if you like, the corresponding facets in the icosahedron don't intersect. Okay, whereas two times that are compatible, like this one and that one, this one and that one, then you know, maybe this edge corresponds to this edge, and this yellow one corresponds to one where they do intersect. Okay, so that was the sort of whole idea, is that the pattern of compatibility is reflected geometrically in the facet structure of the corresponding polytope. And that's already very beautiful. But the pattern of compatibility is a purely combinatorial object, right? Either things are compatible or they're not, and then sets of them are compatible or not. It's a purely combinatorial thing, and we're capturing it by certain geometries. So there's a geometry that's capturing this combinatorics, but that geometry has more moving parts. You know, we can decide where to put the faces, we can move the polytope around, squash it in various ways, and so on. So there is a natural question: is there some way to capture that combinatorics in a way that's completely, totally rigid? In other words, is there some geometric object that captures that captures this whole rich pattern of compatibility in a way that's totally rigid, that doesn't have any moduli, can't move anything? So, and there is, and it's striking, and that's this notion of a binary geometry. So let me just skip to saying what it is for the ordinary case of the icosahedron. So again, if we summarize again what we had, on one hand, I have these sort of variables xij, and in the icosahedron, I have that xij and xkl. So if I have ij and kl on this side, then xij and xkl facets do not meet, let's say, on the icosahedron side. So that's how I'm geometrizing the pattern of compatibility. But as we said, they don't meet, but otherwise there's some freedom in how we can represent the whole polytope. So now we're going to do something else. We're going to associate a different set of variables with each chord. Instead of xij, so let's go back. Instead of xij, bigger pen here. Okay, with every chord ij, I'm going to associate a variable uij. And now I'm going to write down the following cool equation, which is that, these equations are supposed to determine the space of all u's. My equations are that uij plus the product of all KL that cross IJ of UKL is equal to 1. Okay, so that's an extremely simple equation. But first, let me make some comments about this equation. So, if we just quickly do it in the case of the pentagon, for example. Sorry, ignore this slide for a second. If we do it for the case of the pentagon, then I would write down. So if this is 1, 2, 3, 4, 5, it'll be U13 plus who crosses 1, 3? Just 2, 4, and 2, 5. So plus U24, U25 equals 1 plus all plus the cyclic rotations. Okay. So now you see what's non-trivial about these equations. Naively, I have 5 Uij's in this case. 5 U12, U23. Sorry, U13, U24. I have 5 Uij's here, and I have 5 equations. So super naively, these are 5 equations and 5 unknowns, and I would just have some points for the solutions. But remarkably, these equations are not all independent of each other, and in fact, they give us a 2-dimensional space of solutions. Okay, so they're not all independent, and we have a 2-dimensional space of solutions. For instance, we can solve for, e.g., we can solve for U24, U25, and U35 in terms of U13 and U14. Say, okay, so okay, so going back, so these equations are remarkably in general, they actually have an n-3 dimensional space of solutions, exactly the correct dimensionality we need. Okay, and so what is fascinating about these equations is the following. Let's say for a moment we say that the U's are real. So say that Uij are real and positive. Then from this equation, I also see that the Uij's also have to be less than 1, right? Because it's the sum of the product of 2 things that are positive equaling 1, so they all have to be smaller than 1. But then I learned something amazing, that from here I learned that if Uij goes to 0, so if I go to a boundary where Uij goes to 0, then all the incompatible UKLs must go to 1. Okay, just from this equation. All right, so that's quite remarkable. Now we see that we are completely rigidly, in this binary way, we are realizing the notion of compatibility. If I have some variable and I want to go to a boundary where I set Uij to 0, all the crossing chords cannot go to 0. But it's not they can't go to 0, but they go to some arbitrary place. They're forced to go to 1. Okay, so the boundaries, whereas again in the usual polytopic realization, I might have this facet Ij and this facet KL, and okay, they don't meet each other, but where exactly is KL, where is Ij? It all sort of is floppy. But here it's not floppy. It's totally binary. It's highly non-trivial that these equations are. It's highly non-trivial that these equations are consistent. Now, in fact, this fact that the combinatorics can be given this binary representation, this binary geometry is in fact a gauge invariant, and you'll see what I mean by the word gauge invariant description of the worldsheet in disguise. So let me say what I mean by this. So first of all, let me draw sort of index space now. Okay, so here I have I. Let me actually do a specific example. So let's say I have 1, 2, 3, 4, 5, 6, 7, 8. These are indices. Now, when I mean that they're related to the world sheet, I mean that the UIJs are actually very specific cross ratios of n points on P1. Okay. But where is this P1 coming from? I haven't said anything about P1. I haven't said anything about the notion of cross ratio. And a cross ratio on P1 involves 4 points. So where is that 4 in this whole discussion? Okay, so in fact, this is how we discover all of that, beginning from these U equations. The first observation is that you can show, starting from those basic U equations, you can show that the following is also true. So so this is an extension of those U equations. And so here's what you do. So what are the ordinary, one way of thinking about the ordinary U equations is I take 1 point here, 1 and 5. Okay, so I take U15. So that has divided, you see this choice of 1 and 5 has divided all the indices into 4 sets. 1, 5, and the one on this side, 2, 3, 4, and on the one on this side, 6, 7, 8. So I take U15, and then I take, if this region is, let me call it I don't know. I'll just for now, I'll just call it alpha and beta. Okay, alpha and beta. So alpha just stands for 2, 3, 4, and beta stands for 6, 7, 8. I have U15 plus the product of all of the ij's with I in alpha and j in beta of Uij is equal to 1, right? So that's what I mean. All the ones that cross are this guy, that guy, and so on. Okay, so all the ones that are on the complementary regions. But in fact, we can generalize this idea very naturally. Imagine we have any way of dividing the indices into 4 regions. So I'm going to have one set that starts from the index A plus 1 and goes all the way up to the index B. I'll call that this region, all of these guys, A. Then I have another one that starts from B plus 1 and it goes all the way to C. Then I have one that goes from C plus 1 and it goes all the way to D. I'll call this one B. And then D plus 1 going all the way up to A. Okay, and so I'll call this guy, this set A bar, and this set B bar. Okay, so what I've done is just divide all indices into 4 sets. And I'm going to define a U of A, B for any 2 sets as just the product of all the Uij with I inside A and J inside B. Okay, so you just take the product of all the U's with a leg in one set and another leg in the other set. Okay? Then the claim is that all of these guys, as a consequence of those basic U equations, they satisfy that U of AB plus U of A bar B bar is equal to 1. Okay? And so that's a quite beautiful and non-trivial fact that follows from those basic U equations. And in fact, if I label this UAB, this is just now I'm going to label this UAB by the indices involved here, which are little a, b, c, and d. So I'm just going to label UAB is equal to AB, comma, CD. And so A bar, B bar will be So if that's just a label, then there are two trivial facts about these brackets which are true. Just with this definition, one, it's that A, B, C, D times A, B, E, D. A, B, C, D times, A, B, C, E times A, B, E, D is equal to A, B, C, D. That's really trivial, just essentially by definition of what the UADs are. But the really non-trivial thing is that A, B, C, D, exactly this U plus this UAB plus UA bar B bar equation is A, B, C, D plus B, C, dA is equal to 1. These two properties, these are actually the invariant defining property of cross ratios in P1. So that's that's a totally invariant way of saying what a cross ratio is. It tells us that we can think of ABCD as ZA minus ZB, ZC minus ZD over ZA minus ZC, ZB minus ZD. Okay? In other words, this is a gauge variant. I mean, it depends how I represent things. I have to gauge fix the SL2 redundancy with an SL2 redundancy that you're familiar with from thinking about the worldsheet. The actual objects have no such, they're gauge invariant, but these are the sort of deeper gauge invariant facts, just the definition of what a cross ratio is. And so we've seen that we start from the binary realization of the fact that this binary realization of the icosahedron exists, and that binary realization then extended by seeing that it actually implies these generalized U equations, tells us that we can think about the U's as cross ratios, and that gives us a picture of the string worldsheet. Okay, and finally, with or without that picture, we have a very natural notion of a stringy canonical form associated with this U space. I'm just going to, so I'm going to define an integral or a form, but let me just define an integral, which is going to be a function of a bunch of exponents. These exponents are going to, I'll call them xij, which is going to be equal to the integral of the canonical form now on U space. So on the space where the uij's are positive, okay, positive and less than 1. And once again, this integral would be divergent because exactly this canonical form has logarithmic singularities on all the boundaries of U space. But I'm going to regulate it by taking a product over all the ij's, uij to the alpha prime xij. And put an alpha prime to the n-3 in front of the whole thing. All right, so you see, I can define this sort of, once I have this binary geometry, I can define this stringy canonical form, and notice that this has a beautiful property. We've manifested that all the singularities here occur as the xij's go to 0, and they correspond to some uij going to 0. If you wanted to describe this, let's say by solving for the uij's in terms of the z's and giving it a more standard, if you did that, if we solve for the uij's in terms of the z's the way I did a moment ago, this formula would turn into the Kobe-Nielsen formula. Okay. But this is a nicer way of saying it because it makes all the boundaries more manifest. All the boundaries are more manifest associated with the uij's going to 0. And something else is quite manifest. Let's say that one of the uij's goes to 0. Now, even at finite alpha prime, sorry, let's say one of the xij's goes to 0. I'm going to get a divergence from this integral when the uij goes to 0. So I know I'm going to pick up some kind of pole, 1 over xij, multiplied by something. But now comes the crucial point, that even at finite alpha prime, because when uij goes to 0, all the incompatible u's go to 1, these uij to powers for all the incompatible ones just don't give me any dependence on the variables at all. And so I get a clean factorization into the, so if I have an endpoint amplitude, I get a clean factorization into an n1 times an n2 point integral. Precisely because all of those UKLs, precisely because all the U's, so if I'm sending this U to 0, all the incompatible U's, all these incompatible U's are going to 1, and so there's no dependence on their corresponding capital X's, okay? Because this factor for those UKLs becomes 1 to the power of alpha prime XKL, which is just 1. And so they're all irrelevant, and all I get is, what I get is just the clean factorization into this integral associated with the top quadrilateral and the bottom quadrilateral, which was precisely factorization. Okay, so that was very quick, but what I wanted to stress is that the sort of really non-trivial thing is that this binary realization exists, is possible, and then once you have it, once you have it, in the case of the type A, when we can recognize these U equations as telling us that we can solve, we can interpret the U's as certain cross ratios, and we can go back to the picture of the open string worldsheet. If we take the mod squared of these integrals, we get the closed string. We get closed string integrals again at the tree level. But we don't have to go back to the worldsheet. We can just talk about it directly in terms of, in fact, slightly more invariantly in terms of these integrals over the U's. But the crucial thing is that the binary property, the binary property guarantees this binary property that when some U goes to 0, the incompatible ones go to 1, guarantees that we have factorization of these integrals even at finite alpha prime. So not just as alpha prime goes to 0, but even at finite alpha prime. That's a quite magical fact, which is true of this example. But it's true of all of these cluster polytopes. So they all have binary realizations. They all have these analogs of these extended U equations that we talked about. So let me just, and therefore they all have stringy integrals that are associated with them that factorize in exactly the way we talked about before. You remove a node of the Dynkin diagram and you factorize into the product of two lower things, even at finite alpha prime. Okay, so there's a finite alpha prime extension of all of these things that we've, finite prime extension for all these things that we've talked about. But let me tell you what the general structure of these U equations is. The general structure is that for every variable, XA, there's an associated UA, and the equation looks like UA plus the product over B of UV to certain integer powers that are called compatibility degrees. UB/A is equal to 1. So these are not always 1. In the example that we saw before, these were either 0 or 1. Now these can be 0, 1, 2. They can go higher. I think they can even go up to 6 if I remember properly. But for the general Dynkin diagrams, and there's an extremely simple interpretation for what this B/A is. B/A is a Green's function for this quiver time evolution. And the idea is that you start with any old quiver, whatever it's doing, like let's say it was dn, but let's say you start with a variable b here. So let's say b was happened to be a source here, so I would mutate on b, and you set. So then as we time evolve, we'll eventually run into the variable a. So we just want to solve xa is equal to, so furthermore, we're going to just put all those mesh constants, the c's that we talked about, we're just going to put c for b to be equal to 1. In other words, in this first step, when I solve for the next variable after b, I have a formula xb plus xb prime minus something is equal to cb. That cb I set equal to 1. All other c's I set to 0. Okay, so it's like back in our mesh pictures, again, it's kind of like a Green's function. We already saw this idea of the Green's function before in thinking about the Minkowski sum picture before. But anyway, here it's like, you know, in this first step, if my variable b is 1, 3, I would just set this c to 1, and all the other c's I would set to a 0. Okay? Every other c in this picture I would set to a 0. Okay, but then as I go along, I encounter other variables: 2, 4, 2, 5, 3, 5. I'm solving for all of them. Oh, and I set all the x's to 0 as well. Okay, so all the initial x's are 0. Yeah, coming back. So all initial x's are 0. Including xb. CB is 1, so then something is non-zero, and then I just see what I get. So that's the Green's function idea. I'm just turning on a source right in the neighborhood of B, and it propagates out, and the things that I see later have non-zero values. And the non-zero value that variable A has is exactly given, defines this compatibility degree. Okay, so this notion of sort of time evolution naturally gives this idea of a Green's function, and those integers are the ones that show up in this formula. It's an amazing fact that, again, these equations are consistent. They give us the space of the correct dimensionality for the solutions. Just so you have an example what they look like, here's what they look like for another 2 examples of 2-dimensional spaces. The n equals 5 amplitude, or A2, was a pentagon. B2 and G2 are also 2-dimensional examples. B2 ends up having 6 variables. You can think of them as the edges of a hexagon. G2 has 8 variables, the edges of the octagon. And now you see that you get more interesting powers. So in these equations, you can get some 2s and some 3s showing up in the exponent. But what's really amazing is that these equations are consistent. I mean, if I wanted to make equations for the hexagon, and let's say I said that all these powers were 1, I just find the equations are inconsistent, or they only determine points. So these exponents are very special to make it possible to realize the combinatorics of these edges not intersecting, for example, in this binary way. Okay, but this binary realization is possible for all polytopes and for all cluster polytopes, and we also have stringy cluster integrals. They're totally concrete integrals. They're just, it's again the integral of the canonical form for the U space multiplied by the product of all the U's to the alpha prime XA, and there's the alpha prime to the D in front of the whole thing. Oh, where D is the, if I have a D-dimensional polytope. And maybe I should have finally told you what this form is. Remember, the u's go from 0 to 1. So if I write each u as xa over 1 plus xa, then xa runs from 0 to infinity. So the canonical form d log xa is also d log u over 1 minus u. Okay, so the most obvious form that has logarithmic singularities on all the boundaries of U would be, therefore, this omega U would be the product over all A d log UA over, but I have to have a form that only depends on D variables. So a natural thing to do is to take your initial cluster, whatever your initial cluster is, and remember we're demanding that our initial that all of these, sorry, our initial quivers are trees. So I just take my initial quiver that I'm using to define my time evolution, and I write omega u is the product of the d log of ui over 1 minus ui for the u's in the initial quiver. And the answer is the same no matter what initial quiver you choose. So long as it's one of the quivers that allows, so long as it's a quiver that, if I take any orientation of the Dynkin diagram, then I'll get the same answer for this form. Okay, so this is a concrete extension of the canonical form for these polytopes. As alpha prime goes to 0, it reproduces the canonical forms that we've seen. It has a non-zero. They're also interesting at finite alpha prime. They have exactly the same factorization properties at finite alpha prime as the ordinary canonical forms do. And also, as we've seen for type A, B, C, D, as alpha prime goes to 0, they're related to one loop integrands. So we have some extension of field theory one loop integrands with an alpha prime with the same factorization properties and dualities and all the familiar stringy properties, exponential softness in the ultraviolet, which would mean as these capital X's go to infinity, all those things are shared by these objects, but we don't know what they mean yet at finite alpha prime. And we really don't know because very little has been explored about what these integrals actually look like at finite alpha prime. They've only sort of just been defined back in December, and very little work has been done to actually try to compute them, try to compare them to what we know about open string one loop amplitudes to see, are they the same? Is this just another formulation for what the open string amplitudes look like? If it is, then there's nothing that looks like a worldsheet involved. You know, this DN cluster polytope, which is what would give us one loop, doesn't seem to have anything in it that has a torus, doesn't seem to have any theta functions, any of that stuff that we normally see. But it's not completely insane that it might be a different way, a very different way of talking about the integrand for open string. So okay, so I will leave it at that now and ask if there are any questions.
Yes, I have a question. This expansion of the stringy integrals in terms of loops, do you have a similar expansion in terms of genus somehow? I mean, for the stringy.
We're going to be talking about that just now.
Oh, okay, thank you.
Any other questions? Okay. Do you want to take another very quick break song, or should we? No, actually, why don't I go on a little bit, and then maybe we can take a break before we come back to the cluster algebra review. Is that okay?
Sure.
So
Whatever you want.
For another maybe. When did I start the second session again? I don't quite remember.
No, I don't remember either.
Okay, fine. Then I'll just keep on going. Okay. All right. So now we're going to move on to the story at we're setting up the story at all loop order and all orders in the 1 over n expansion, and talk about the connection with cluster algebras and this the more general notion of clusterhedra, which of course includes the things that we talked about before, but figures out how to extend them for these more general cases. So first, let me make just the 0th order comment to begin with, is that what did we do even at tree level? We started off thinking about planar Feynman diagrams. Right? And that planar Feynman diagrams, because at tree level, that's tree level, the single trace terms, that's what they are. Every diagram is a cubic diagram that we can draw on a plane. Okay. So now in general, when we go to higher loops, we start off life drawing Feynman diagrams just abstractly as graphs, but of course we know, since a Tuft, that it's useful to think about embedding these diagrams in two-dimensional surfaces. Okay, so these diagrams can be drawn on two-dimensional surfaces with various genuses. And in fact, if we have a Feynman diagram with H traces, then in L loops, then the one-to-N expansion is an expansion in genus where we draw the diagrams on a Riemann surface of genus G. And if there are H traces, we imagine that the Riemann surface has H little boundaries in it. And each trace has a trace of a product of a bunch of things. So each boundary is a bunch of points. Okay, so we have some, maybe we have some torus, but if it's a 3-trace piece, we would have 3 boundaries. And if each one has a bunch of points on it, this is trace TA1 through TAN, TB1 through TBM, TC1 through TCM. Okay, so we'd have these multiple trace pieces on it, and then we're supposed to draw Feynman diagrams that are embedded in this surface. Okay, so that's the usual Tuft expansion. And what we've done here from the very beginning is just draw the dual of these things. Okay, so instead of talking about cubic graphs on a disk, we're talking about the triangulation of, so instead of cubic, and by the way, so the cubic graphs on the disk we can think of as a sphere with one boundary, right? So we have one boundary, and so what we have, I mean, these are all very simple things that I just want to be explicit once. So when we draw this is the same as having a sphere where we take this sort of boundary, where we added this boundary component. Okay, so these are topologically, I mean, exactly the same thing. So, but what we're doing is drawing the duals of these diagrams. So now, having embedded the diagram on a two-dimensional surface, the notion of a dual is unambiguous. Okay, so we can draw a dual, and what we get from the dual is a very simple bit of, I mean, it's very analogous to the standard Tuftian counting. What we get from the dual is a triangulation of the surface with the same number of with H boundaries of its H traces, the same genus, but in this triangulation we'll have a certain number of punctures, where the punctures is related to the genus and the loop order by this simple formula. Okay. Now this is very simple to derive, but instead of just deriving it abstractly, let me show you how it works in an example. Okay, so here's an example of a two-loop vacuum graph. So it's very simple. We don't even have any boundaries at all. So H equals 0, and the graph that I've drawn on the left can be drawn on a torus. Okay, so genus 1, and so here's my torus. Now, as I've labeled it, just we can just see where A and B in the graph go on the torus. Okay, and so I've drawn the torus as my little fundamental region here, and I've just copied it many times just so I more easily see what is going on. Okay, so this is unfolded infinitely in both directions, and so you can see that indeed the sort of connectivity of A and B in this picture is faithfully reproduced by what I've drawn. So I've just drawn that picture on a torus. Now, let me, so I started with the double line notation. Let me just shrink all these lines. So again, that's what we did before. We just drew these cubic Feynman diagrams. So when I shrink all these edges, okay, now I have just these blue lines. I have exactly the same torus, exactly the same picture, but now I want to draw the dual of this picture. So that means that I put a point in the center of all the faces. So all these sort of quadrilaterals now have this star in the middle. and then I connect them with edges in exactly the way we normally do when you have a dual. So here there's a line, there's the blue line, so I put a green line between them. Here there's a blue line between, so I put a green line, and here I connect them up like this, and so on, right? So this would copy in both directions. But what is this second picture? The second picture is also the triangulation of a torus, but the torus now has one special point on it. It has one puncture, this star. So this is a triangulation of a once punctured torus, and it's a triangulation in terms of two triangles, this one and that one, and of course if I can unfold all their copies, but in the fundamental domain it is a triangulation into two pieces. Okay, so and that's a special case of this formula. Okay, when L was equal to 2, I go from this diagram to the triangulation of a once punctured torus. All right, so let me skip this for now. So in general, then, what we're interested in is, ignore the right-hand side just for a second. I'm just about to come back to it. But tree amplitudes are triangulations of a polygon. Okay, triangulations of a disk with some marked points on the outside. Single trace one-loop amplitudes are triangulations with a puncture in the middle. Single trace two-loop amplitudes are something with triangulations with two punctures in the middle. Okay, and anything, I mean, just everything is, so if I take some two-loop amplitude and take the leading 1/n correction, then I would draw it on a torus like so. Here is my boundary where my n points live, so it's a single trace again, but it's the leading 1/n correction, so I draw it on a torus. So it's this particular triangulation of a Okay, so we can think dually about the sum over Feynman diagrams as a sum over triangulations of surfaces of genus G with some specified number of punctures, where the puncture is related to the number of loops by this formula.
Sorry, Nima, is there a number of external legs here?
Yeah, the number of external legs all goes into the H trace. Okay, so each component, I should have said this. Each trace component is a boundary with n points on it, with some number of points on it. Mm-hmm. Okay, where whatever you have in that trace. So if you have a component that looks like trace TA1 through TAM, then I'd have these points A1 through AM on that boundary.
And the number of punctures only depends on H, not on this side.
The number of punctures depends on L and H. It depends on the loop order and on H, exactly. Okay. So just to do another example, if I'm interested in, one loop double trace. Okay, so this is something that's not leading, but sub-leading, right? In 1/n, one loop double trace. If I have things that look like trace TA1 through TAM, trace TB1 through TBJ, then I would be triangulating an annulus, where I'd have on the outside, I have my points A1 through AM, and on the inside, B1 through BJ. And then I have to triangulate this surface. We'll be talking about this example in more detail. Okay, so this is just this is a very basic extension, just a very basic dual of the usual genus expansion. Are there any questions about this?
Nima, in the two loop case, you had this D tilde n plus 2 in the next page, I think.
Yes.
Is that like a forward limit of the Dn? Is like a somehow forward limit of a one loop?
Yeah. Well, so we'll see how the boundaries are related to each other. But this is really sort of the fact that it kind of it happens only, like, two loop is the last thing which is affine. And then beyond that, it's just different. I mean, they're not, yeah. So we'll be talking quite a lot about, well, if we get there, we'll be talking a lot about those things. But for now, I just want to sort of set up what the problem is. What we're trying to do is, what we're trying to do is look at the duals of all, look at duals of Feynman diagrams, which are triangulations of punctured surfaces. And what we saw at tree level, and even at one loop, is that triangulations are, the individual triangulations are captured as vertices of these beautiful polytopes, and that we could think about what those triangulations, we could think about where those polytopes came from by just, I mean, let me just summarize what, you know, if we look at this example, or even this example with a puncture, okay? So here, on the one hand, we have triangulations. These triangulations are thought of as sort of vertices of the corresponding cluster polytopes. But in turn, they had a sort of a separate description as, you know, coming from positive wave equations in kinematic space. So these are sort of three related things, right? It's non-trivial that the triangulations of surfaces can be captured as vertices of any polytopes at all. And it's also interesting that these polytopes that if we're not even thinking about triangulations, we're just looking at all these variables, these xij variables, or the extension of these variables, so this case with the surface. Here, we find some kind of kinematic space just associated with these arcs. There's a kind of a notion, slightly abstracted, of time evolution or a wave equation in these kinematic space. And the positive solutions of that sort exactly give us the same polytopes whose property, whose vertices are triangulations of these surfaces. And the canonical forms of these polytopes give us the corresponding integrands for the scattering amplitude. Okay, so that's the more general thing that we're trying to now understand. So we want to understand for any Riemann surface with punctures, can we associate with it? Is there any? So first, what are the variables? What are the analog of these? What's the analog of the kinematic space? What's the analog of all the triangulations? Is there a polytope whose vertices captures all the triangulations? Or if you like, whose vertices would give us all the Feynman diagrams dually? And is there something like a wave equation in kinematic space, or some analog of that, some analog of a simple underlying picture giving us the analog of the ABHY cluster polytopes for these examples? Okay, so that's the question that we will be thinking about. So now what I want to do is and up to this point, we've managed to avoid talking in any serious way about the underlying cluster algebra structure. But just for a few minutes, I want to give just a high-level motivation for why cluster algebras are relevant to this question, and just give a zero third, a big picture of where we're going. And then we'll take a break, and I'll come back and I'll just give you the sort of crash course on cluster algebras. So you can understand what the ideas involved are in more detail. And then finally, we'll talk about what these clusterhedra look like and what the ideas are that go into them. So I just want to take a few minutes here just to give you this sort of high-level overview of why cluster algebras have anything to do with any of it. So we'll come back to these things in more detail. For now, it's just slightly impressionistic. So what are cluster algebras? Well, you begin with any quiver, and so again, a quiver is just it's just a graph with some oriented arrows, and you can have more than one arrow. Okay, so you have a very general quiver like that. And then there's a notion of mutation at a vertex V. So you also associate variables, these x's with all the nodes. And then there's a notation of mutation at V, which is the following rule that will be motivated. I'll motivate it more later, but anyway, in fact, I won't even say this in detail now. There's just a way to get another quiver where you take your vertex, you reverse all the arrows, and then there's a few other things that you have to do in general. The rule that we had before is a special case of a mutation when you only have a source. That just involves reversing all the arrows. In general, it doesn't have to be just a source, it can be a source for some arrows, a sink for others. So there's an extension of these rules that I'll talk about. And what makes it an algebra is you also get to solve for a new variable in terms of the old one by this interesting nonlinear formula, that the product of the old and the new variables is the sum of the product of all the w's going in to the vertex V and all the w's, everything going out and everything going in, the product of all the variables. Now, we didn't see anything that looked like this nonlinear formula before, but in fact, but we did see something that looked like x plus x prime minus the sum. Okay, so we saw expressions like that, and these expressions are actually closely related to these nonlinear ones by a process known as tropicalization. I'll say a little bit more about it later. But anyway, so there's an algebra associated with it, and we can solve for new variables in terms of old ones in this way. And so you can then, again, you can start off with a quiver, you can mutate, and you can ask, what do you get? Sometimes the algebras are, sometimes you keep on going, and everything is finite. As you keep on mutating, you find the variables come back to the original ones, and the quivers come back to the original ones, and so you get something finite. So these finite type cluster algebras turn out to be associated with orientations of Dynkin diagrams. Sometimes it turns out that the next worst thing that can happen is that the shapes of the quivers that you get come back to themselves. So there are finitely many shapes to the quivers, but the variables keep on going forever. So the variables get more and more complicated as you go on. And then the kind of wildest case of all is that where both the quivers get more and more complicated and the variables get more and more complicated. This infinity is the generic situation. So I'll come back to say a little bit more about the distinction between these two kinds of infinity in a moment. But again, this is just at a high level. Now, here's a motivation for this picture. And a motivation for this picture actually came from thinking about triangulations of surfaces. And again, we'll talk about this in more detail as well, but just quickly, let's say you start off with a triangulation of this hexagon, which I've drawn here. So let's look at this triangulation. And associated with this triangulation, you can get a quiver. And that's done in the following way. You put a point in the middle of every edge of the triangulation, also including the ones on the outside. But the ones on the outside are different because they're on the outside. So maybe I'll put those with little square arrows. And then inside each one of the triangles, you draw in turn a small oriented triangle that goes between the points that you've drawn. So here, all with the same consistent orientation of the surface. So I would draw that guy, here I would draw this guy, and so on, okay? And so if I only keep the nodes inside, if I forget about the ones on the outside, then associated with this picture, I get a quiver. I can keep the ones on the outside if I want to, but the most invariant part of it is just the quiver associated with the ones on the inside. Now, the pretty thing about this, and we'll draw some example. Well, I might as well do this example now. Let's do an example of. So let's say I do this hexagon. So if we do this one, let me draw this guy's associated quiver. So this would go like this. Actually. And then, so this is 1, 2, and 3. Then at the level of the triangulation, it's kind of natural. At the level of the triangulation, it's natural to think that I can go from this triangulation, from any one triangulation to another, by taking a quadrilateral inside the triangulation. So here's a quadrilateral inside the triangulation. So I've taken the square and I've broken it into two triangles by adding this diagonal. Well, it's natural to ask what I would have gotten if I do the other diagonal. Okay, so that means that I would have instead this triangulation. Okay, so so this guy on the left, I have this quiver. So with this guy on the right, what do I have? With this guy on the right, let's again put our so that's my triangulation. Let me put these points in the middle here. So okay, so now I have something that looks like one. So this is my new variable here. Let's say I've gone from this one. So I've replaced this chord with a new one. So I'm going to call this new variable there. I'm going to label it 4. So I went to 1, 2, 4, and but now let's just look at the 1, 4, 3 here. So let's look at the direction of the arrows, and now you see that they're now like this. Okay, so I have 1 to 4, 4 to 3, but I also have 3 to 1. Okay, so from here, so let's see if we can learn what the rules are. I've gone from one triangulation to another triangulation. At the level of the quiver, I've gone from this triangulation. I've gone from this quiver to that one, where I've replaced 2. And so let's see if I can abstract away what I've done. Well, clearly, first of all, I've reversed all the arrows. I've reversed all arrows into 2. Okay, so from here to here, I reverse the arrows. But there's this extra arrow here from 3 to 1. And you can think, what is the purpose of that extra arrow? Well, it's that on the left, I used to be able to go from 3 to 1. I used to be able to go from 3 to 1 via 2. And I don't want to forget about the fact that I could have done that. So because I could have gone from 3 to 2 to 2 to 1, I want to add an arrow between 3 and 1 to record the fact that that beforehand I could have gone from 3 to 1 via 2 as an intermediary. Okay, so so already in this example, if we want to capture what happens to the triangulation as we flip a diagonal of the quadrilateral, if we want to capture what that's doing at the level of the quiver, we have to come up with these rules for how I have to change one quiver to the other. And the rules are exactly the ones that I summarized here. So you to mutate at a vertex V, you reverse all the arrows. If at V there was an A that could go into V and a V that can go into B, then you should add an A that goes into B. And finally, something we didn't see in this example, but which is quite natural, is if you just see 2 arrows going forward and backwards, you just delete them in pairs. Okay, so these sort of bubbles are not doing anything. You just delete them in pairs. So that is the rule just for mutating the quiver. The rule for the motivation for this interesting product formula. It's also possible to motivate nicely, but let me not talk about that one now. Okay, so in other words, thinking about triangulations of surfaces was the first an early motivation for thinking about these more general mutations for more general quivers and cluster algebras. And actually, even that nonlinear formula is actually very prettily interpreted in terms of the Skene relations. So if you want to get what that nonlinear formula is for the product of two cluster variables, well, whatever the arcs that would go along with those cluster variables, if they cross each other, that means that those two arcs can't show up in the same triangulation. So they're exactly these sort of incompatible variables, just like the ones we've seen before. And the mutation just says that the product of two arcs is the sum of opening the two arcs up in the two different ways, as we're very familiar with from Skene relations and from many places. So this is a nonlinear formula, right? It says that the product of the old one and the new one is the sum of the product of the two of them, which have been disentangled in the two directions. Okay, so those are cluster algebras, and there are various remarkable properties of cluster algebras that are true for all the triangulations of surfaces, as well as, in fact, for all quivers, period. But there's some extra special things that are true for triangulations of surfaces that we'll be talking about in more detail. Okay, but just to finish this sort of high-level discussion before we get into the details, if you remember in our previous picture, something that was important was sort of keeping track of how I could expand every x that I saw how I could expand every x that I saw in a basis of the original x's of some initial quiver. Every variable that I saw, the sort of vector that records the expansion in terms of the initial variables is called a g vector, and two different variables have two different g vectors. So it's a way of it's a canonical way of labeling the cluster variable. And in fact, so this is true for any cluster algebra. So if you begin, we begin with some initial quiver, sometimes called initial seed, and there's some initial choice of cluster variables, x1 through xn. Then every other variable is associated with a vector, and I can think of that as telling me how to expand, some capital X that I was associated with any other variable in terms of the initial seed. Now, it turns out that, remember before we saw these relations x plus x prime minus the sum of everything going out of all the w into v, or out of v of xw. And that's because we're only talking about mutating on sources. In general, if you have something which is has both arrows going in and out, both of these relations are interesting in principle. Okay, so both the ones where it's sum over all the sources going out, as well as the ones that are going in. And it's a beautiful fact that that the g vectors actually satisfy one of these two relations. Okay, so these are linear relations. This is just linear algebra. But once you give me a choice of initial seed, every mutation is associated with a pair of these expressions. I can keep one of the pair and throw the other one out. And those are a bunch of linear relations between all of these variables that are exactly satisfied by the g vectors, and they in fact determine the g vectors. So one way of sort of phrasing what's going on is, once you choose an initial seed, for every mutation we have two linear relations. So you choose one of the two, and if you randomly choose one of the two, then the set of all these relations will be horribly inconsistent with each other. But it is possible to choose one of the two in such a way that the set of linear relations are all consistent, and those linear relations, when they are consistent, uniquely determine all the new variables, all the vectors associated with the new variable. They're called g vectors. Okay. Okay. So let's call this big set of relations that depend on, of course, they depend on the initial choice of cluster. So there's just a bunch of initial relations. There are a bunch of these linear relations, having chosen my initial cluster. I'm going to call this whole set of relations R. Okay, so And so the first interesting fact is nowhere here have we said anything about kinematic space, wave equations, so on and so forth. But there's a remarkable way in which the kinematic spacetime emerges from this cluster algebra. And this is how it works. Consider all of these relations that we see, this whole big set of relations. For every single mutation there is one of these relations. Okay? There's this giant set of relations, but it turns out that there's a tiny subset of these relations, so let me call them R star, that generate all of the others by positive linear combinations. What I mean is, it's just a purely linear algebra statement. Every one of these relations can be expanded in terms of a basic set of relations with positive coefficients. Okay? Now, this has nothing to do with visualizing anything or drawing a kinematic space. This is just a completely abstract fact about the set of all these relations. The set of all these relations are generated by a small number of them. Now, it turns out that those relations which are the generators, are precisely what we were in the case of AN calling the meshes in the kinematic spacetime. So what I mean, so I can illustrate with this example. So let's say I have all these, so here's one relation that I would have. All of our Gauss's law relations from our kinematic space picture are examples of these x plus x minus x minus x relations. So this relation A, B, C, D, this is a relation, but we know that that relation is actually a linear combination of this one plus that one plus that one plus that one. Okay, so this fact that just abstractly all of these relations can be expanded in terms of a basic set, a much smaller basic set of ones, is in the particular case of the story of type A, is the fact that we can think of the relations associated with big meshes as being local sums of the little ones. This is a non-trivial fact. Just abstractly, the set of all relations tells you that it can be organized in a way which is captured by the basic mesh relations being put together in a picture of a local space-time in kinematic space. But I'm phrasing them in this more abstract way because this is a fingerprint of something interesting happening. The set of all relations are not independent and they're generated by a small set. Okay, so that's one sort of high-level comment. Another high-level comment has to do with a very general way in which the very basic features of space-time and quantum mechanics are actually captured by the cluster algebra and the G vectors. And in order to explain this connection, let's first just ask something again, going back to a tree level. Back at tree level, we have we begin by just thinking about all of our kinematic variables. Okay, so who are all of our kinematic variables? They're all the chords on this polygon. Okay, all of our kinematic variables are chords on this polygon. And we can think of them as propagators xij. And now there is something interesting that I can't just put these propagators together randomly, right? The ones that come together, I'm only allowed to talk about ones that come together like a triangulation of the polygon. And those are, we think about as space-time processes. So there's already something interesting. Given each variable randomly, okay, so why am I considering just these sets together that look like triangulations of the polygon and are dual to space-time processes? So that's one question. That's sort of the origin of locality, is why do I only care about these things coming together in particular combinations? That's the first thing. The second thing is that quantum mechanics tells us we have to add all of these diagrams together. Okay? And we have to add them all with a +1 coefficient, all equal coefficient, because of quantum mechanics. So already in this little example, the locality in space-time is the fact that I only care about particular combinations of these propagators together. And unitarity, quantum mechanics is the fact that I have to add all of them together. And why would I do either one of these things if I didn't know that I cared about locality in space-time or quantum mechanical unitary. Okay, and in fact, there's a beautiful fact about the geometry of all of these G vectors that tells you should do both things. Okay, and here's the fact. So this is an amazing and deep fact about any cluster algebra. As far as I know, it does not have a simple, one-line conceptual proof. All of my cluster friends that I talk to tell me, yeah, it's a deep fact. But here's the fact. So every cluster variable is associated with some vector. That's these G vectors that I was telling you about. By the way, again, just to keep some intuition, if I go back to the icosahedron case or even the other cluster polytopes, each G vector is also the normal vector. Remember, all the faces of these generalized icosahedra are associated with the xij variable. Let's say for the icosahedron, all the faces are associated with xij, and the G vector associated with the face is just the normal of that facet, the normal vector associated with that facet. Okay? So every one, that's in the finite type case, but in general, even for arbitrary cluster algebras, every cluster variable is associated with a G vector. And now here's the remarkable thing. First of all, if I just take this group of vectors, so if I draw sort of a two-dimensional example, well, we saw an example already. We saw an example that looked like this. We saw an example for the G vectors for the particular case of A2. It looked like this. And you see there's something kind of cool here. If I just handed you this set of vectors, you would notice that there's a good reason to put 1 and 2, group 1 and 2 together, group 2 and 3 together, group 3 and 4 together, right? The cones that are produced by these G vectors are non-overlapping. 1 and 2, 2 and 3, 3 and 4, 4 and 5, 5 and 1. These are non-overlapping cones, A, and B, in this case, these non-overlapping cones actually tile and cover all the space. There's no holes in them, okay? Now, the general statement is the following. And first of all, this is a statement in finite type, and I'll come to just the little modification in infinite type. The general statement, true in this example of the icosahedron, is that the things that correspond to local space-time processes, in other words, or equivalently triangulations of the polygon, those G vectors are actually the vectors for minimal cones among this set. Now this is living in higher dimensions in general, but this all set of vectors, I shouldn't take random collections of them together. They actually come together naturally in small cones, and local space-time processes are these G vector cones. Okay, so there is something special about the set that come together that we interpret as local space-time processes. They're the basic cones in this picture. But on top of that, why am I adding them all up together? Well, because the cones naturally all come together. It's remarkable that they're non-overlapping, and together the cones tile the entire space. So the structure of the G vectors of the cluster algebra is telling you that what the interesting combinations are, local space-time process, and they're telling you that they have to be considered all together. If you leave any of the cones out, you're putting a hole in this otherwise beautifully tiled space. And this is something beyond words, because it actually tells us something immediately about the projectivity of our forms. If you remember, I told you in very early on that it's a non-trivial fact that it's possible to assign signs to the wedge product of the d logs of all the x's to make the answer projectively invariant. Well, this is a reflection of the fact that all the cluster cones fit together snugly, and they tile space. And in fact, the practical thing is it tells you what the formula is. It tells you what the sign is. So what you do is you go to any cone and you take the d log of all the x variables associated with each one of these vectors, and you weight it with the sign of the determinant of the g vectors that go along with them. Okay? And if you do that, then it's very simple, essentially trivial to see. The fact that the cones are all tiling means that all the projective variations cancel in these interior boundaries, and you just get something that's perfectly projectively invariant. Okay, so that's the first comment. Another comment is that another interesting thing that we saw was that it's possible to pull back the form to a subspace such that on that subspace you get the amplitude where all these +1 coefficients. Okay, so now why does that happen? Well, here, where's the obvious subspace we should pull the form back to? Well, we should just take every variable xa and just expand it in terms of the initial set. That's the most natural thing that we can do with coefficients given by these g vectors. So this is my subspace in general. xa is g dot x plus some constant. Okay, so that defines subspace. And if I just pull back this previous form on this subspace, then I end up getting just the product of all these of all the initial dxi's multiplied by the sum of everyone with a +1 coefficient times the product of all the 1/x's, which is exactly the amplitude. Now, why did this happen? This happened because of another cool fact about these g vectors. Each g vector, each one of these cones, I told you that they're non-overlapping, but on top of that, the determinants that you get for each of these, every cone, the determinant of the g's, of the g vectors in this cone is ±1. And because it's ±1, when I take this previous projective form and I pull it back to this subspace, I don't get any numerical factors here. I just get the sum of everyone with a +1 coefficient. So the projectivity of the form and the fact that it's possible to pull back to a subspace to get the amplitude is a consequence of this deep fact that the cluster cones, that the g vector cones associated with the triangulations actually tile space. Finally, what is the ABHY story about? The ABHY story is that this is all great at the level of the form, but I might like that if I pull back to this subspace, that actually on this subspace, if I ask for all the x's to be positive, that on this subspace, I really see the cluster polytope. In order to see the cluster polytope, these constants k have to satisfy some, if you just did it directly in this way, the constants k have to satisfy some seemingly complicated inequalities between each other in order for it to work. And the ABHY construction is precisely guarantees that combination of inequalities is satisfied. In fact, it thinks about it in a different way. And if you begin with the ABHY construction, you can even sort of read it backwards in order to understand why these G vector cones are non-overlapping and so on. So in this finite type case, we could really go back and forth between these various pictures and decide sort of who is primary and who is the and who is the derivative. But just at this just to summarize this high-level discussion, so I've told you two things. One of them is that the picture of the kinematic space naturally comes out as an abstract feature of the relations in this cluster algebra. So if you give me the set of all mutations and I look at these linear version of the mutations, only one of these two pairs of the linear x plus x minus x equations are correct, are consistent. If I take this consistent set, there's still an enormous list of mutations, but there's one remarkable fact: this huge list is actually generated by a finite set. And the finite set is exactly the one that has an interpretation in terms of elementary meshes that fit together into this local picture of a kinematic spacetime. So if it maybe sort of bugged you before, why did I draw that kinematic spacetime picture? How did I know? This is why I said in answer to an early question, it depends where you want to start. If you want to start abstractly with these sort of cluster algebraic ideas, then it actually comes out, quite remarkably, it comes out that this kinematic spacetime is the answer to the question of who is the basis for all the relations between these cluster variables. Okay, so And that idea also works for all the rest of the finite type cluster algebra. So every one of those ABHY realizations of the polytopes, you can think of as the logic is, you first look at all the relations, then you look at the basic relations that generate all the rest of them, and then you simply take all those basic relations and set them equal to positive constants and demand that all the variables are positive. That's the generalization of the positive wave equation, and that gives you all of these cluster polytopes for the finite type case. Okay, so that's one basic idea, that there's a guiding principle that of all the possible relations, we should look at a simple set which generate all the rest, and that's somehow associated with dynamics in the kinematic spacetime. That's one idea. The other general point, even without talking about the polytope, just at the level of the scattering form, is these sort of deep, simple things about the projectivity, but these deep, hidden things about the projectivity of the form, and the fact that it's possible to pull back to a subspace where you get the amplitude. These are actually reflecting a simple and deep fact about the G vectors of the cluster variables, and that's what I just said already. That every triangulation of the polygon, or which means every quiver that you ever see by mutating, all the quivers that you see by mutating are called clusters. I don't think I said that before, but anyway, all the quivers that you see by mutating are called clusters. Every cluster is associated. The variables you see in a cluster, each one has a G vector, and the ones you see in a cluster are actually minimal cones. And if you take all the clusters together, they're non-overlapping and they tile all of space in the finite type case. And that fact that they're the minimal cones and they tile space is the avatar of locality and unitarity. But they're somehow come together as a very simple feature of these of the G vectors for cluster variables. Right. So that I hope is some motivation that it's worth trying to understand this cluster structure better, and that we should try to. So there's something deep tied. The fact that there's a cluster structure associated with Riemann surfaces is with punctured Riemann surfaces. That's the novelty. Okay? That's something that I mean that was not known, before the story of cluster algebras emerged in the mid-2000s. So even something that seems like very well-trod mathematical territory, there's something new and sort of deep underlying. There's some deeper underlying structure to the story of Riemann surfaces and triangulations of Riemann surfaces. And so we're going to try to understand what these G vectors are, and so understanding it is clearly going to be important for our general program of finding these analog of these clusterhedra for higher loops. And just to say this last thing, and then we'll take a break. Almost all of these comments that I talked about apply to infinite type cluster algebras, except for the following: the G vector fan. In other words, if I take all these cones, it's still true that they're non-overlapping, and it's still true that there's no sort of holes in the middle of the space. However, they don't collectively cover all of space. So there are some regions that are missing. Let me draw some pictures. So if you look at this cluster algebra, and we'll be talking about this guy, then it turns out that its G vectors look something like, so if this is the initial cluster, maybe you get another one, and you get another one, and you get these like, and then you have something like this on this side, another one, another one. So you get these skinnier and skinnier triangles, but so they almost cover all of space, but there's sort of one direction that they're asymptoting to. And so they don't quite cover everything formally. Okay, that there's one direction, so it's lower codimension, but there's one direction which is not covered by any of these codes. We'll be talking about this example and actually, if I go to the next case, just with something like that, then there's even a whole hole. I mean, there's a region like this which is covered. So this is covered by cones, just like what I drew. But there's a whole hole here which is not. Okay, so that means that there are things sort of beyond the cluster variables that you have to start thinking about if you want to understand what is going on. That's the first challenge. But it's still true. I mean, it's not true that it's some crappy thing that there's sort of random holes everywhere. Everyone fits together snugly, but they fail to cover the whole space. Okay? So they're getting skinnier and skinnier, and they fail to cover the whole space. Again, we'll talk about this in more detail. Now, there's another remarkable fact, which is that if you just abstractly talk about quivers and cluster algebras, as I said, you can just ask when do you get something finite, and you get something finite when it's when the quiver is an orientation of a Dynkin diagram. So when do you get something where the quivers come back to themselves? So the quivers are finite, but the variables keep on going forever. Remarkably, it turns out that happens essentially only when there's a few exceptional cases, but only when the quivers correspond to triangulations of surfaces. So I find that quite amazing that this idea of triangulation of surfaces, if you never care about surfaces, you haven't thought about surfaces, triangulation of surfaces is actually a natural part of this whole subject. Surfaces emerge as the answer to the question, what gives you finite quivers, even if the variables can keep on going forever, okay? So that's one very special thing about surface cluster algebras, is that the kind of quivers that we see are of finite shapes. The quivers are in fact in bijection with the Feynman diagrams, if you like. So they're the duals to the Feynman diagram. So that's the fact that on a given surface we have a finite number of diagrams that we can draw. But again, it's not our desire to think about surfaces or diagrams. This is just an answer about this abstract question of what mutations look like and when we get the same quivers back over and over again. That's one remarkable feature of surface cluster algebras. The other remarkable feature is that they don't have these holes. They do have this feature where you have directions in which these cones asymptote, but they don't have these big gaping holes in them. And so that makes it even more sort of special to try to figure out what these directions are, how to think about them, and what it means for the physics. Okay, so all right, so that's the sort of that's the challenge, and so I've given you some high-level reasons that you should care about the cluster structure, but perhaps we can stop there for now and ask if there's any questions.
So Nima, each cone is still maximal dimensional even in this infinite.
Yes, that's right. Each cone is maximal dimensional, but what happens is really like in this, and we'll see it in more detail. But what really happens is that they get skinnier and skinnier, and there's some particular direction which is just not officially covered.
Okay.
Okay. So maybe I can ask you guys about timing. How should we proceed? I mean, I'm happy to keep going. It is now around 11:30 your time, right?
Yeah.
Okay. So so what do you want to do? I'm really happy to do it. I mean, I'm happy to keep going. If you guys are exhausted and you would rather not, that's, I mean, even if you're not exhausted, if you'd rather not for any reason, we can stop here. I mean, again, anyone who's really interested with zero obligation, I'm happy to like pick it up again tomorrow or some other time. If you want, we can keep going now. If you want, I don't have to pick it up tomorrow. Whatever people want.
How much? I mean, you can certainly go on for now for sure, but how much time do you think you can or is it?
Well, I mean, I think I wanted to I think okay. Let just. I think it's probably about if it's going to be useful. I think I wanted to give a self-contained introduction to cluster algebras.
Yes.
And that's probably like an hour and a half. And then after that, these clusterhedra are probably another hour and a half after that. So I don't want to keep people to like 2:30 a.m. But yeah, so just tell me whatever you want. Alternately, I could just if you want me to do much more impressionistic things, I could do that too. But I thought for the people who might be interested in the cluster algebra stuff, because it is this sort of it's a not trivial to penetrate literature. So I thought people might find it useful just to have it summarized in a useful way.
So I think the Utin is here. So, but is it? Maybe you can do like the first 1.5 hours today, and
great. I'll do that.
And maybe tomorrow tomorrow.
Also, there's literally zero obligation. I mean, I'm not.
But it would be nice to see the physics application also, right? So.
Okay. Yes.
Yeah.
All right. Great. Then why don't we do the cluster algebras 101 now, and then
tomorrow.
For the really diehard people who want to see, we can do it tomorrow or Friday or whenever.
Yeah. So you did. Is that okay?
Yeah, I'm here. Yeah, sure.
Okay.
Yeah, that's fine. That sounds perfect.
Yeah.
Great. Yeah. So I'm happy to start anytime, whenever you want.
Yeah. I think we can start.
Okay. Excellent. All right. So so now so we're just going to do some. I'm going to talk about some basics about cluster algebras. So just a quick definition, just so you know what I'll be doing. I'll talk about the definition and some simple examples. Then we'll talk about G vectors in general. And then I will tell you a lot about surface cluster algebras. Sort of essentially everything you need to know in order to be able to play with surface cluster algebras, effective ways of computing the G vectors and so on and so forth. So, how to draw triangulations for weird surfaces. So this is all all very practical. Okay, so let's start with the definition. So to begin with, we're talking about quivers. So let me first say some generalities on quivers. So given any quiver is naturally associated with an antisymmetric matrix. A quiver ij is equal to plus nij if there are nij arrows from I to j, and minus nij, otherwise nij arrows from j to I, and 0 otherwise. Okay. Now we're not going to need so ij is going to run from 1 to n, where n is the dimensionality of our it's going to be dimensionality of our algebra. Sometimes people like to talk about adding frozen nodes. So these are going to be nodes that you never mutate. We saw examples of this, for example, when we talked about triangulations of the polygon. When we did this example, let's say we have these guys. These are unfrozen nodes. We can mutate these things in the middle. The guys on the outside were, we never touched the boundaries of the polygon. So sometimes it's useful to have these extra variables that are called frozen variables. More generally, instead of having an antisymmetric matrix, then we have a bigger matrix that's called the B matrix associated with the quiver, BII, which is n by n plus f dimensional. Okay. Where we have f of these frozen nodes. So we're not, as I said, we're not going to need this much, but Okay, and so but we still have there's still a natural way to, and also we don't care about arrows between these blue guys. We don't care about arrows between the frozen guys. So if we just had an ordinary quiver, then we would have an anti-symmetric, we would still have a matrix where we know how to fill in the entries with pluses and minuses depending on whether the arrows are going in or out. In greatest generality, generality, what we want of this matrix B is that it needs to have the property that Bi little j, in other words, if we just take this block, B little j is what's said to be anti-symmetrizable, which means that I can make it anti-symmetric by rescaling its columns. Okay, so in other words, that there exists some set of alpha I such that AI little j equals alpha I Bij is equal to negative alpha j Bji is negative Aji. So that's what it means that it's anti-symmetrizable. And in fact, in order to give, you can represent any B. So any B matrix is represented by, can be represented by giving these alpha I for every node, and then we have an antisymmetric Aij, and Aij represented graphically, okay, as usual. Okay, so I mean, I'm just saying something trivial, that this B matrix is just defined by being alpha rescaling, let's say, a column multiplying by alpha I up to an antisymmetric matrix AI. Okay, so that means that I can represent the most general situation by a quiver with variables also attached, numbers which are these rescalings attached to the nodes. Okay, so this would be a normal situation. Maybe they're all 1. So then, but I could also have 1. I could put a 2 there. I could put a 3 there. Okay, and these numbers are just representing. So if this is vertex 1, vertex 2, vertex 3, vertex 4, then this is just saying that alpha 1 is equal, well, all the alphas are equal to 1, but in this case, alpha for vertex 2 is equal to 2, alpha for vertex 4 equals 3, and so on. Okay, I don't want to spend too much time on this because we're not going to be using it that much, but it does show up. So, okay, now what is the rule for a mutation? The rule for mutation is whatever this number is, alpha in a vertex V, doesn't matter. However many arrows we have, if I have some W3 arrows going out or in W1, W2, I reverse all the arrows. I don't, these alphas never change. The alphas never change. So I just, I reverse all the arrows. So now there's W3 incoming, W1 incoming, W2 outgoing here, okay? And I have the other rule that we had talked about, which is that if I have I with an arrow going into K and going back into J, then I also have to add, oops. Then I also, I have to, if this is what I had before, I have to have a new matrix where the delta I, where the change in Aij, so whatever arrows I had between I and J, I don't care. I don't know what I had, but the change in Aij is equal to alpha K whatever that number was there, multiplied by aik akj. If all the alphas were 1, this is just a rule that we talked about before, where if you have an arrow like this, then you have to add that arrow. And this has to be done for every pair. So if I had 2 arrows here and 1 there, then I would add 2 arrows, because I could have gone from here to there via the top arrow or the bottom arrow. So in general, if I have m arrows here and n arrows there, I'd add mn arrows. And that's exactly what this rule is capturing. Okay, that rule is capturing, and with this extra decoration with the alpha k. All right. So I've now defined. So given a quiver Q, initial quiver Q, there's a B matrix BII, which is equal to alpha, if you like, alpha I inverse times AII. So given a quiver, I've defined this, and now mutation. I've told you how to get a new quiver from an old one. I've told you what the rules are for. I've told you the rule for quiver mutation, and finally, the formula is xk. The formula for mutating the variables is xk times xk prime is the product of all the i's for which aki is greater than or equal to 0 of. So you take all the arrows coming in, and the ones that come from any vertex with an alpha k, you raise it to the power of alpha k. The alpha k aki plus the product of all the arrows going the other way. xi to the negative alpha k aki. And notice here, I could have also just written this as bki. bki. So the data is a certain n by n plus f anti-symmetrizable matrix, and there's a rule for mutating at a vertex to get a new quiver, a new matrix, and new variables given by this formula. Okay, anyway, that's the abstract definition. Let's now just talk about let's quickly talk about examples. So as I said, so some examples. So first, again, just examples of what the rules are for mutating the quivers. So let's say I had this quiver. We saw this example before. Let me just do it again. And if I want to mutate at 2, sorry, I don't know why I keep saying that. If I want to mutate at 2, then the new quiver that I would get, and here all the alphas are 1. So from now on, we'll mostly talk about alphas equal to 1. Then I reverse all the arrows, and I have to add an arrow from 1 to 3. So now I get x4. So that is the new arrow, and my x4 satisfies that x4, x1 is equal to, there's something from the left coming from x1, sorry, x4, x2 is equal to x1 plus x3. Okay, so x4, the new variable I get is x1 plus x3 over x2. Okay, here's another example. Let's do this classic, simplest, smallest non-trivial example. Is the A2 cluster algebra, where what I begin with, my initial cluster is x1 goes to x2. I won't draw the circles for the nodes. I'll just draw the variables there. So let's first mutate on x1. If I mutate on x1, then I get x3 with the arrow going into x2 Well, let's do the computation for x3. So x3 times x1 has to equal, well, all the arrows coming into x1. There are no arrows coming in, so it's something raised to the 0. So I just get 1. And then all the arrows going out of x1, so I get plus x2. Okay, so I solve that x3 is equal to 1 plus x2 over x1. Okay, so let me put this up here. So this is 1 plus x2 over x1. All right, so let's keep going. If I now mutate at x2, oh, sorry, I should have said it's very easy to check that the mutation squares to 1. Okay, so if you mutate and then mutate again at the same vertex, you come back to where you were started. So that's why there's no point in mutating again at x3 because it'll just take us back to x1. But we can mutate at x2, and then you can just keep working it out. I won't. I'll just tell you the answer. You get x3, and then now you get a more complicated expression: 1 plus x2 plus x1 over x1 x2, which is x4. Let me call this x4. Okay, and now I can mutate on x3. So let me now mutate on x3. Let me send it here. So now I'll have x5 and oh, sorry, I apologize. I want to keep going here. I mutated x2 to turn into x4. Let me just write it down properly. x2 went to x4. Now I'm going to mutate on x3. So here I switch again. So now I'm going to have some x5 and an arrow coming in x4. And x5, if you do the calculation, turns out to be 1 plus x1 over x2. And then quite nicely, if you mutate on x4, you find that you get x5 with the arrow coming out into x1. And now, so in other words, you come back. After you mutate x4, you actually come back to x1. And now when I mutate x5, that comes back to x2. With the arrow coming out of x1 into x2 again. All right, so that's not obvious ahead of time that if you do this process that it closes, but in this case it does close. And in fact, you can represent the whole chain. So each one of these quivers that you get as you mutate, every quiver gives you some collection of variables that come together. That collection of variables that come together is called a cluster. So this would be the initial cluster. This would be the initial cluster. And then there are various other clusters that we see along the way. But we can see that all of these clusters are associated, can be represented on the vertices of a pentagon. This is exactly the same as the statement that the triangulations of the pentagon can be represented in this way. But in this case, we're labeling them with clusters. So this would be the initial cluster 1 to 2, and then so here, so the vertex is a cluster, and two vertices are connected by an edge if you can do a mutation to get from one cluster to another. So in this case, I mutated at 1 to get 3, so I have this one, and then this vertex was 3, 4, this vertex was 5, 4, and this vertex was 5, 1.
Can I ask a question?
Yes.
So in this picture, are there no non-mutable variables? I mean, the frozen variables?
Yes, in this case, there are no frozen variables. Exactly. And mostly I'll be drawing things with no frozen variables. I just thought in the first few minutes I'd give you the most general definition. Yeah, I mean, the frozen variables are conceptually useful for many purposes, but I mostly won't talk about them today.
Okay.
Yeah, so there are no frozen variables.
In the previous example where you had like 3 clusters, 1, 2, 3. So can can x1 and x3 be frozen variables? Because you are mutating on x2, right?
No, here I just mutated on x2. I could keep going. I could keep going and just so in other words, this is just illustrating This is just illustrating the rules for mutation. But I could keep going and mutate on all of them. In fact, I invite you to try it in this example. Okay, in this example, if you start with this guy, and you just keep mutating. Well, first it's pretty easy to see what shapes for the quivers you'll ever see. Like, for instance, let's say we had mutated at x1, then I would have gotten this guy, right?
Yes.
So it's pretty easy to convince yourself all the shapes you'll ever see, all the quivers you'll ever see, either look like this, you know, some orientation like that, or one of these things with a loop. Okay, and different orientations. But the really cool thing is if you start with this guy and you just mutate, you'll find that you run into a total of 9 different expressions. Okay, just like we saw here. By an expression, I mean like you know, they're all some expressions in terms of the initial variables, and you'll find 9 different expressions. So they'll all come back. They'll all be fine. You'll find a total of 9 expressions, 6 more other than x1, x2, and x3. So x1, x2, x3, and then 6 non-trivial ones. And you'll find that those 9 only show up in a total of 14 clusters. Okay, so yes. Now those 14 clusters are the correspond to the 14 triangulations of a hexagon, or the 14 Feynman diagrams for 6-point scattering. Okay, and the total of 9 variables are the 9 chords of the hexagon, or the 9 propagators for the 6-point. But that's not non-trivial ahead of time. When you start, it's not obvious that it's going to come back, that it and you know what you're going to get, and so on. So that's the sense in which cluster algebras give a larger setting in which we can ask this kind of question about that we saw for the case of triangulations of the polygon. In the case of triangulations of a polygon, we have a collection of objects, triangulations, and they're naturally related to each other. We can imagine whether it's possible to make them vertices of some polytope where 2 vertices are connected by an edge, if I can get from one triangulation to another triangulation by flipping one diagonal of a quadrilateral, right? And the story of cluster algebras lets us put that kind of question in a much bigger setting. Now we have a much larger collection of combinatorial objects, all these quivers and their associated variables tied to them, which are all the clusters. And so we can ask, what do we know about all these clusters? Is there some kind of geometric object that captures all of them, such that every vertex is a cluster and 2 vertices are connected if there's a mutation that takes you from one cluster to another?
Okay, thank you.
Okay, did that answer your question?
Yes, thank you.
Right, and again, already here we see the sort of most primitive example of this, simplest example, that indeed there are a total of 5 clusters in this example, and the 5 clusters do beautifully fit as vertices of this pentagon. Again, this is the perfect analog of what we saw. I mean, it's exactly the same as the thing that we saw for triangulations of okay, so all right, so that's the simplest example. We'll come back to say more about this example. But let me again just say some generalities. You can, just, you know, x1 and x2. And here you can check, and we'll talk about this in more detail, that this, here the sort of quivers that clearly just go back and forth, right? There's nothing that can happen. But here the variables go on forever. The variables go on forever. Okay. Here's another example of the same thing. So here's another algebra. Here's another quiver that looks like this. This is another interesting one. This also goes on forever for the variables, but still finite quivers. The only quivers you ever see are that shape, and it turns out that if we mutate, so let's see what happens if we mutate on this guy. If we mutate on this guy, then I reverse the yeah. So let's say I take this picture and I mutate on him, then what I get is this. Okay, so I have a picture that kind of has a loop like this, but with two arrows now. Why is it two arrows? Because I have to add an arrow from, if there's 1, 2, 3, I have to add, because I could go from 1 to 2 and 2 to 3, to add this extra arrow from 1 to 3. So that's, so when I mutate on 2, I'd have 1, 3, and let's say 4 here. Okay, so these are the only kind of shapes of quivers that I get in this example, but the variables keep on going forever. On the other hand, if I have this kind of quiver, so here's a simple one. Here, it both goes on forever for variables and infinitely many different quivers. So all these things are possible, and as we said before, the ones that are associated with the ones that are associated, the ones that are finite are associated. The quivers or orientations of Dynkin diagrams. And by the way, the ones where there are Dynkin diagrams that are not simply laced, so the ones with 2 arrows or 3 arrows, like in G2, those are exactly the cases where you need this more general B matrix, where the alphas matter. So the alphas can be 2 or 3 in those examples. Okay, but we're not.
Can I ask a question?
Yes.
So can you show the previous diagram that you wrote with the triangle?
Yes.
So this quiver, I can imagine it being the mutated version of just 1, 2, 3, right? Without that link between 1 and 3. In the one, I mean, so 1, 4, 3 just before.
Yes.
So and because mutation squares to 1,
yes.
I can think of this as going back to just like a straight line. Why do I get like a double link?
Oh, sorry. You mean why do you get this double link here? Are you asking why you get? Oh, sorry. 1 second.
I mean, so in the previous example where you had a 1, 2, 3 quiver and then you mutated 2 to get 4 over there.
Oh yeah, no, but the terms are not quite the same. So let me draw them side by side so you see what the difference is. Okay.
Okay.
Yeah. So if I understand properly, you're asking the following. You're asking about the difference between this example, right? You want to compare this?
Yes. Yes.
Okay. Good. Okay. So let's look at these. So let me erase the arrest here. Notice. It's a very important difference that, yeah. So in the previous case, I was doing something like this. And so let's add this guy. Okay. So this is what I was starting with. Okay. And so when we mutate a 2, exactly the same thing is happening, except now, because there was already an arrow there between 1 and 3, I always have to add. I mean, if there was something that goes from 1 to 2 and 2 to 3, I always have to add another arrow between 1 and 3. Doesn't matter if there's one there already. Now there happens to be one there already, so now there's going to be two there. Okay, so now I reverse the arrows into 2, but now I have to add one more arrow.
Yeah, good. Okay, okay.
Okay? Are you happy?
Yes, 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 yes.
Okay, great. All right, so, okay, good. So let's now, okay, so that's a tour of some examples. See if there's anything else. Okay, so there's one general, there's one general remarkable phenomenon. Something remarkable is known as the Laurent phenomenon. And that is something that we've seen in all these examples, but which is not obvious a priori. You notice that in all these examples, like, let's say even in this A2 example, you'll notice that every single time, every single variable that I got, actually, you might naively have thought that the denominators, I'm always dividing by something when I get the new variables. You might naively think that the denominators could be some more and more complicated polynomials in the initial variables, when I write everything in terms of initial variables. However, we see that the denominators are always just monomials in the initial variables. Okay, we don't get something like 1 plus x1, x2 downstairs. We just get x1, x2. So it's said more invariantly. This is a remarkable fact. It's not obvious, but it's a remarkable fact that every cluster variable is a Laurent polynomial. In other words, it's just a sum of monomials with positive or negative coefficients. Okay, it's a Laurent polynomial in the initial cluster variables. Okay, so that's a very important general fact. Okay. All right, and that's going to be yeah, we're going to use that for a variety of purposes. Now, let me pause here and ask if there are any other questions. Now we're going to move on to talking about G vectors.
Nima, just a curiosity. When in the diagrams where you were talking about those double, I mean, for the cluster algebra for the two loop kind of a thing, how do you check that you have an infinite number of those? I mean, if you could go a few pages behind, I can point out what you're talking about.
Yes.
Yeah, this one. No. Just go down further, further. Yeah, this one. Yeah. So how do you said there are infinitely many quivers here. How do you check? I mean, you can, if there are a finite number of quivers, you can check that. But how do you check that there will be an infinite number of those?
Excellent question. The way you check. I mean, all these things are non-trivial, and all these things are like, you know, mathematics that's of order a decade old. So this is all, you know, this is all. I mean, maybe I should have made this general comment beforehand. It's not directly related to the question, but just to say it. The story of cluster algebras is not some on-the-shelf, done, completely understood mathematics that we're then just going to use. It's a very active area of current research in math. And so, you know, it could well be that trying to figure out the connection to physics in all the different guises will actually help a lot in understanding better how we're supposed to think about it, even mathematically. And I should also have said that I'm talking about one aspect of the overlap between cluster algebras and amplitudes that's naturally associated with these triangulations of surfaces. There's a whole other story that connects more general cluster algebras. In fact, the positivity associated with the positive Grassmannian is a cluster algebra structure on the Grassmannian, is related to a cluster algebra structure on the Grassmannian. And if we think about the kinematic space that we talked about in the first few lectures, just for n equals 4 super Yang-Mills, we are really invited to think about it as associated with a cluster algebra on the space of the external momentum twistors. So it's really sort of amazing that that in all these kinematic spaces, for both for n equals 4 and for the bi-adjoint theory, there seems to be some important cluster structure associated with it. And in fact, literally, this picture would be related to like G48, for example. So, but just coming back to your question, how do we know? Well, we know only because, you know, an order a decade ago, maybe less, but of order that the time scale, Dylan Thurston and friends classified all of the finite type cluster algebras. So we know what they all are. And they're all triangulation of surfaces, and you check this is not a triangulation of a surface. So so that's how it's done.
I see. Okay, thank you.
Okay. All right. Okay, so let's now move on. And I'm going to talk about G vectors. And there are a variety of ways of defining them. I'm going to give one general definition, which is not the most primitive one. It's a somewhat derivative one, but I don't want to talk about frozen variables and coefficients and so on, and it's not crucial. It's not crucial because, at least for our purposes, we'll be talking about surfaces. I'll give you a separate direct way of determining G vectors on a surface. We're going to have a lot of fun in a moment drawing triangulations of surfaces and so on. Okay? But I want to give a motivation for this idea of G vectors, is that we somehow want to label all cluster variables in some unique way. Okay, and let me come back to this example. If I come back to the example that we just saw, this A2 example, okay. If I look at all the variables, let me just write them down. So we had x1, x2, x3 is 1 plus x2 over x1, x4 is 1 plus x2 plus x1 over x1, x2, and x5 is 1 plus x1 over x2. So we notice that again it has this Laurent phenomenon, and what I can do, what's something kind of interesting to do is let me imagine what is the sort of leading term in these expansions as the initial variables x1, x2 goes to 0. Okay, so obviously the initial one is x1 goes to the x1 to the 1, x2 to the 0. Okay, so and x2 is going like x2 to the x1 to the 0, x2 to the 1. So I'm going to associate these with the obvious sort of basis vectors 1, 0, and 0, 1. But if I look at x3, x3 goes, the leading thing as x1 goes to 0 is just x1 to the minus 1, x2 to the 0. So I'll associate this with the vector minus 1, 0. x4 is, the leading term again would be x1 to the minus 1, x2 to the minus 1. So I'll associate this with the vector minus 1, minus 1. And x5 would go like just x1 to the 0 and x2 to the minus 1. So I associate this with 0, minus 1. Okay, so these are not G vectors. They're all, for obvious reasons, denominator vectors. Okay, but already if we plot them, there's something kind of nice happen. So if I look here, here's like x1, and if this is the x1 and x2 axis, this would be x1, this would be x2. What is x3? X3 is minus 1, 0. So this is 1, 2. X4 is minus 1, minus 1. And x5 is 0, minus 1. And you still see the sort of phenomenon that we saw before quite nicely. You know, this kind of cone is one of the clusters because x1 and x2 are in a cluster. x2 and x3 in a cluster, x3 and x4 in a cluster, and so on. Okay, so that's kind of cool. These vectors do label the they do nicely label the cluster variables, and also geometrically they carve up the x1, x2 space into cones, and every cone is in fact the x's in that cone belong to a cluster. Now, G vectors are a more invariant notion of this idea. Okay? G vector. So let me choose my initial cluster. And so it's associated with some B matrix. Okay, B, I. So remember, I choose my initial cluster, and then there's this matrix that's N. If I've added frozens, doesn't matter. We mostly haven't, but if I add them, I have this antisymmetric B matrix. So this is N plus F column vectors. So for instance, if we literally do our simplest example of A2, the B matrix would be 0, 1, minus 1, 0. Okay, so this is column 1, 2, 1, 2. All right, no frozens, nothing else. Now, so the idea of the G vectors is the following: take any variable x, and we've just said by the Laurent phenomenon that we can it's expressible as a sum over monomials. So M alpha is a sum over monomials, and every monomial is written in terms of the initial cluster variables to some power. Okay? And again, this is our compressed notation where this V alpha is a vector, right? So this is x initial 1 to the V alpha 1 up to x initial n to the V alpha n. Okay, but I'm writing in this compressed notation, if you like. Okay, so what we did before is kind of randomly choose randomly order these vectors V with respect to whether they had the biggest powers of x1 and x2, the biggest negative powers of x1 and x2. That's how we ordered them. That was sort of a random choice. But it gave us a way of choosing out of all the monomials, we choose one of them, which is going to label the variable. But there's a more natural way that you can order them as follows. So we can say that a vector VA is smaller than a vector VB. So this is our definition. A vector VA is smaller than vector VB if we can write VB as equal to VA plus a positive sum of the columns of the B matrix. So this B matrix is a bunch of n-dimensional vectors, and so what we're asking is whether it's possible to, if it's possible to write VB as VA plus a positive combination of those guys, then VB is sort of more positive than VA. And then what we're going to do is take the smallest of all of these V alphas. So by this definition of greater than, we're going to take the smallest of all the V alpha associated with this vector, with this expansion. So maybe I should have called this X to remind me that it was the expansion for variable X. Take the smallest of all the V alpha for X, and that's defined to be the G vector for the variable X. Okay, so the G vector is like the denominator vector, except your notion of what's leading is more invariantly given by the B matrix rather than just randomly caring about what the powers of x1 and x2 are. Okay, so let's see how this works again. If we go back to our example. Okay, so if we go back to this example, let's now not talk about let's work out what the G vectors are now. Okay, so Okay, so again, the g vector for x1 would just be 1, 0. That's all I have. G vector for x2 would be 0, 1. That's just my basis. But now let's look at x3. So x3 is, we have x1 to the minus 1 and also x1 to the minus 1, x2. On my B matrix, remember here is 0, minus 1, 1, 0. Okay? So let's, the corresponding sort of exponent vectors would be minus 1, 0. And here would be minus 1, 1. Okay, but now I want to compare minus 1, 1 and minus 1, 0, and to see whether I can write one as the other plus a positive combination of the columns of the B matrix. And so here it's clear who is bigger, because minus 1, 0 is equal to minus 1, 1 plus sorry, I did it wrong. Sorry, I apologize. The B matrix is 0, 1, minus 1, 0. That was the arrow's going out. I just copied it down wrong. Okay, so now minus 1, 0 is minus 1, 1 plus 0, minus 1. And that's that column. Okay, so from here we see that minus 1, 0 is bigger than minus 1, 1. And therefore, the G vector for x3 is equal to minus 1, 1. Okay? Is that clear? So I can record that. The G vector for x3 is minus 1, 1. And let's quickly do the other ones. Let's now look at x4. So x4 is a little bit more fun. So for x4, we have the vectors minus 1, minus 1, minus 1, 0, and 0, minus 1. Okay, and first of all, we can see that 0, minus 1 is equal to minus 1, 0 plus 1, 0 plus 0, minus 1. Okay, so these are the two columns there. So we see that 0, minus 1 is bigger than minus 1, 0. And also, and also minus 1, minus 1. Minus 1, minus 1 is minus 1, 0 plus 0, minus 1. So that 0, minus 1 is that column of the B matrix. So also minus 1, minus 1 is bigger than minus 1, 0. And so we learn that the G vector for x4 is equal to minus 1, 0. Okay, so you see, out of all the monomials in x4, we found the one, minus 1, 0, that was the least relative to this metric determined by the B matrix. Okay, so and so similarly, we can finish. I won't do it. I'll just give the answer, but I think you'll see how it works now. So GX4 was minus 1, 0, and it turns out GX5 is 0, minus 1. Okay, so those are all the G vectors in this example. And again, if I plot them all, I get this a similar picture, but not exactly the same, but a similar picture that looks like that. Okay, so this was x1, x2, x3, x4, and x5. And not coincidentally, this is exactly the picture of the G vectors. This is exactly the picture that we saw for the normal vectors to the facets of the ABHY pentagon. Okay, so as I said already, these are those are G vectors. Okay, so that's one definition of G vectors, and there is this. There are other definitions of G vectors, but there is this remarkable fact that we've seen in these examples, but I'll say again that that if I take the G vectors in any cluster, I can get what you can call a cluster cone. The cones are non-overlapping, and they tile space with no holes in finite type, and they almost and they still cover all of space. Well, there's still no holes. They all snugly fit together one after the other, but they can leave holes open in general infinite time. Okay, so okay, so that's the definition of G vectors, and a few examples. So any questions about that? Okay, let's see. All right, so then if you're not all collapsing, let me just go on, and I'll say a few things about surface cluster algebras, and then we'll stop. Okay. Okay, so now let's talk about the surface cluster algebras. And so here we're sort of imagining a very general picture. I'm drawing a disk with a boundary inside, maybe some punctures, some points on the outside, points on the inside. Okay. And we want to talk about triangulations of surfaces. Okay, so we want to talk about triangulations of surfaces. To begin with. So, so before talking about triangulations, I want to make some more basic definitions. Because, I mean, of course, we all knew what we meant by a triangulation when we drew like a disk or a polygon. But in general, the triangulation is going to look a little weirder. It's slightly less intuitive to always draw them. That's one of the practical things I want to tell you how to do. But well, let me first give a sort of more, sort of a slightly more invariant, more abstract definition. The first, an arc, we're going to define an arc is any path up to homotopy. In other words, I can move it around continuously, any path up to homotopy that is not homotopic to a boundary segment. So for example, this guy would not be an arc because that is homotopic to a boundary segment between these two marked points on the boundary, 1, 2, 3, 4. That is not an arc. This is not an arc. I mean, similarly, this is not an arc, but this is an arc. This is an arc, and so on. Okay, so that is an arc. Next, we say that two arcs are compatible if they don't intersect, except maybe on the boundary. They don't intersect except at boundary. Now, to do this, you might have to, this should be true of some homotopy representative. And just what I mean by that is clearly, so here is, well, here are two arcs actually. So let's say 1, 3. Actually, let me remove this puncture for fun. Let's say 1, 4 and 1, 3 are clearly compatible arcs, but I could have been sort of dumb and drawn this homotopy equivalent of 1, 4. Okay, if I do that, it intersects 1, 3 a bunch of times, but it didn't need to intersect 1, 3. Okay, so there is some homotopy representative 1, 4, which does not intersect 1, 3. Okay? Okay, and so finally, a triangulation is a maximal collection of compatible arcs. So in other words, arcs that are all compatible with each other and where you can't add one more arc and keep everyone compatible. Okay? So that is a triangulation. So a triangulation in this way refers to this whole collection of arcs. I haven't told you what the triangles are, and you can define the triangles. Let me just put the definition up here. So I mean that's all you need for a triangulation, but let me just define the notion of triangle. A triangle is just a collection of 3 arcs involving less than or equal to 3 vertices. A closed collection. I mean, it's a closed loop. Let me call it a closed collection, or a closed loop of 3 arcs. Involving at most less than or equal to 3 vertices. Okay. Oh, I should also said that our surfaces are orientable. And I'm always imagining kind of a clockwise orientation for the whole surface. Okay. Okay, so first of all, so that gives me a notion of the triangulation, and every triangle T inherits this orientation. I mean, of course, I know what this orientation means for each triangle. So I'm giving these sort of very reasonable seeming but kind of abstract definitions, but we'll see in examples in a second. Okay, so okay, so far this is just the notion of a triangulation and triangles. So let's draw some of them. So for instance,
can I ask a question?
Yes.
Do the arcs necessarily have to be hinged at the boundary?
No. We'll talk about other the ones in a triangulation
Right.
do because as we'll see, if you imagine a loop inside, then the
Right.
loop inside will sort of cross everything. Okay.
Right.
Will cross a lot of things. The guys that are loop inside are going to play a starring role in the story of Clusterhedra later. Okay. But no, but the sort of arcs that we're talking about, the arcs that we're talking about, they don't have to go to the boundary. For example, they can go from one
Puncture to another.
Exactly. We can have punctures to another, or we can even have loops going around some numbers of punctures and so on. Okay, we can have things like that. Okay, so we don't ahead of time say that they have to reach the boundary. We just apply this definition. But from this definition, it's clear that any closed loop in the inside is never going to be participating in a triangulation.
Right.
Okay. All right. So let's do a few examples. So if we do the kind of things, just the simple thing. Here's an arc, and then a maximal collection. I mean, I just have to add another guy. For example, I can add this guy, but now I can't add anyone else. Okay, now I can't add anyone else, and my triangles are obviously these triangles. Okay, so so that's a that's a trivial example. Let's do a more interesting example. More interesting example is actually this is an annulus. Let me call this point 1 and 2. Okay, and now let's see what some of the arcs are in this picture. For example, I mean, I can have this. That is an arc. This is an arc. Yeah, so or it could wind around like that. Okay. By the way, what about this? If I have 1 and 2, what about this guy? Is this an arc? That is not an arc because I can homotopically translate it out, and it's the same as this boundary segment. Okay, but if I had another point, like this guy, if I had another point on the outer boundary, then this would be an arc. Okay, because now I can't. Now the point 2 obstructs me from being able to take it out. All right. So, okay. So, but in this case, the only arcs that I have are just the only arcs that I can have. And already you see something amusing here in this very simple example. This is going to end up being just a 2-dimensional cluster algebra, but I have infinitely many variables. So I have this one. I can wind around any number of times. I can wind around any number of times the other way as well. Okay, so those are all the arcs. But now let's look at a triangulation. So for instance, here's by our definitions, I can add this arc and let's say this one. Okay, so
so in this case, why aren't the two arcs homotopic to each other? Is it because they are winding? I mean,
yes,
the second one.
It's precisely because they're winding. Yeah. So this guy is not homotopic to that one. Yeah. It's precisely because of the winding.
Thank you.
Yes. Absolutely. Yeah. And the story of the winding is going to be the whole story essentially about the clusterhedra and so on. That's why it's good to see it work in these simple examples already. Okay. So from here you see that we have 2 arcs and I can't add any more, right? So this is already supposed to be a triangulation. But let's draw this triangulation. Let's sort of figure out how to think about this triangulation. And you see that they're kind of pretty degenerate triangles. Like, I mean, you can kind of see a triangle here. You can kind of see this triangle. That's one triangle. And then we're going to see, and we see this triangle. Okay, but let's learn. Let me just give these things some names. Let me call this X and Y. Okay, and now I want to talk about how we see these, how we think about the triangulation. So let me first take one of them. Let me take this. Oh, sorry, I didn't give all the arcs names even. So let me draw it like this. So I called this one, I don't know, X and Y. And let me call this big arc on the outside, I don't know, gamma, and this arc on the inside, and the arc on the inside, alpha. So those are arcs. They're boundary components. Okay. So all right. So I want to figure out how to draw this triangle. I mean, clearly it looks like sort of a degenerate triangle, but the easy way to do it is to focus on the edges. So it's a triangle, so there's supposed to be 3 edges in the triangle, right? So what are the 3 edges of this? What are the 3 edges of this triangle? They're of course X, Y, and alpha, right? But now I want to draw all of this on a plane. The whole point is that we can draw this triangulation as just really a bunch of triangles on the plane, perhaps with some identifications. But we can really draw them all on the plane, and I just want to tell you practically how to draw them. So in order to do it, the sort of crucial thing is to remember that there's this orientation. So we have this we have this clockwise orientation everywhere. So let me just draw what that little orientation looks like in every pair of places where the edges meet. So here's where X and Y meet. I'm going to draw, there's an orientation like that, which means that whatever the triangle is, where X and Y meet, I should have this line coming in from X and out of Y. Okay, and so there's the points 1 and 2. And so that's where one pair meet. Now, so let me draw that here. So here's like X and Y. So now I'm drawing a flat version of this. Okay, so there's X coming in into 1 and going out of Y. Okay, now Y goes to 2, and there it meets alpha. So Y meets alpha. So now this is alpha. And how does that go? Well, we're coming in again, clockwise orientation. So going in there and coming out. So but that's fine. That's consistent here. So that's in from Y, out with alpha, back at point 2. And now I'm going on alpha, back where alpha intersects X. So I'm going from alpha from 2 back to 2. But again, all that matters is that alpha is intersecting X there. So this is going in through alpha and out through X, which is also correct. So in through alpha and out through X. So you see I have a consistently oriented triangle in here, but it's a funny triangle where two of the vertices are identified. Okay, so that is the picture for this triangle. And we can draw the analogous picture for this blue triangle out there. So how would I draw the picture for the blue triangle? Well, in the blue triangle, let's say up here again, I have in X into 1 and in from gamma and out to X. I have here, let me start from here, for example. I have from Y into X, from Y into 1 and out. I'm drawing all of the points. So finally here I have in through Y and out through X. Okay, so always I drew that one backwards. Just a second. So over here, this orientation says that this orientation says that it's in through X, out through Y. Okay, on this side. Oh, oops. Okay, so this is what we now get. Oops. Let me just draw it. Okay, so let's see why this makes sense. So here, so in this corner we have gamma into 1 and out with X, and that's just what we saw here. Gamma into 1 out with X. Over here we have X into 2 out in Y. That's correct. X into 2 out in Y. And finally, at the bottom, we have in with Y, out with gamma. That's where Y and gamma intersect, which is this one, in with Y and out with gamma. Okay. So that's it. So you see that the top one was our green triangle. The bottom one is our blue triangle. And indeed, it is a triangulation. It's a triangulation. They're non-overlapping. They cover the space with consistent orientation. Okay. Notice that we have some edges identified here. So the way I've drawn it, x is an interior, I mean, x and y are just interior boundaries, but gamma and alpha are real boundaries. So this is the point one. But here, the y's are identified on these sides. Note that every variable is going to occur as a diagonal of some quadrilateral inside the triangulation. This is an important general point. Every variable, we can mutate every cluster variable, and a mutation is just always taking a quadrilateral in the triangulation and flipping one diagonal for another. So in this picture, if I wanted to make it, so here I've already made manifest. So let me just draw it again. Here I've made manifest that x is the diagonal in some triangulation. But if I wanted to make manifest that y was, if I wanted to make this manifest for y as well, I can just extend the picture with the identification, right? So for instance, I could draw it like this. This is just a practical matter. So this already covers the whole space, but nothing stops me from, for instance, continuing this like so. So this is y, x, y, and x again. I mean, this is just like, you can unfold a torus however much you want. If I do it like this, so I have these identifications now. Y is identified with y here, x is identified with x. Any two triangles in this picture is, gives me a non-redundant covering. But if I draw it this way, it's manifest that if I want to do a mutation on x, I can take x in this quadrilateral and flip it for that one. If I want to mutate y, I can take y in this quadrilateral and mutate it for that. Okay? So just to give you an example, which is slightly more fun, I won't do the whole thing, but just so you see that why it's useful to, so you don't have to think and sort of visualize things. If I have, here's a case with the, anyway, an annulus with two boundaries on the inside, and here's a triangulation. And now you see you can't add any more triangles. But just to stress how funny it can be, if I call this guy on the outside gamma and these guys on the inside alpha and beta, then there is a triangle in this triangulation with only one vertex, one, okay? Okay, so there's that triangle, but you don't have to sort of sit there and imagine doing anything with it. We just follow exactly the same rules. Who are the, if this guy on the outside is x and y, then the edges are gamma meets x, or gamma x and y. And then we just have to look, where does gamma meet x? Up here. So gamma meets x, going in with gamma and out with x. So it's the orientation. So that's why I draw it like this. Okay, in with gamma, out with x. This is the point 1. This is x, and then x goes back to itself and meets y, and it meets y in from x, out with y. Okay, so in with x, out with y, again the point 1, so this is the edge y, and I get the same thing on the other side. So this is a legal triangle. Okay, this is a legal triangle, just one vertex, 1, 1, 1. Okay. But I can read it off from the picture. Always, the idea for not thinking is just look at the three edges and go to the corners where they meet, draw the orientations, and then just draw the corresponding orientations on the picture so it's oriented the same way. All right, so any questions about what a triangulation is? All right, I just have just two more things to say, and then I'll let you guys go. But
and
yes.
there is this another way where you could insert like just look at this doubling of the the external points. Like you just draw one at the top of the disk that you drew, and then you could draw one at the bottom. And then instead of looking at the x and y arc that you have, you could look at x as coming to the left-hand side of the annulus and y at the right-hand side from the bottom.
Yeah.
It's the same thing, but it's just somehow maybe easier to, I don't know, visualize, or I mean.
Yeah, I mean, different people find different things useful. I mean, well, of course, it's clear what's going on. If we take this one, we might imagine breaking it up into two very nearby points, and then we get a triangle, right?
Yeah.
So that's fine. I'm just telling you from experience.
Okay.
That's the way I wanted to most intuitively think about it, but you then end up spending a long time if you're looking at even slightly complicated examples, just doing a lot of visual imagination, and there's no thinking involved. I mean, it's really a completely mindless process. That's just so I'm just trying to explain it as the mindless process. But indeed, it's exactly what you said. I mean, we can think about this triangle as kind of splitting up one into a one here and a one prime there and a one double prime there. And then we do get a triangle.
Yeah.
It gets trickier when you have many points like this, and there's one vertex, and you have to split up in different ways for different quote unquote triangles. So that's when it gets trickier. So this way of talking about it makes it mindless. Okay, so that you just.
So Nima, you also had these marked points inside the surface when you started with the surface cluster algebra. You had this configuration of marked points which was just inside the surface, which was not sitting on either of the boundaries.
Oh yeah, those were punctures. Those were
punctures.
punctures.
Sorry. So those so far they have not.
I haven't drawn them yet. I'm precisely coming to the issue about punctures now. Actually. Okay. But let me yeah. So far I haven't drawn anything with punctures. We're going to come to punctures in just a moment. Okay. So. Right. So let me. So now we've seen what a triangulation is. Now, given a triangulation, from a triangulation, I want to get a corresponding quiver. That is going to be the quiver for the cluster algebra. And the rule is just the following. For every triangle, we have an orientation. So for every triangle, we put a point in the middle. And then we do so in other words, there's going to be a variable associated with every arc. And for every triangle, if we have our clockwise orientation, we also draw, we put a point in the middle of the arc, and then from here we get a quiver. So for example, let's do the example that we just talked about. Let's see how we get the quiver for this guy. Okay, so okay, so we just saw that so this is x and y and gamma and alpha. We saw that the triangulation looked like this. So what we're supposed to do is put a point in the middle of all these guys. Also, I mean, the gamma and alpha would be frozen. So let's just add them for fun. So there, and then we just draw our oriented triangle. So then we just draw this and Okay. But if we now just see what the arrows are, here we have X and Y. And you see there are two arrows between X and Y. There's one arrow here and there's one other arrow there. So we have actually two arrows between X and Y. And and if we wanted to keep track of alpha and beta, we would have, let's say, alpha and gamma. We'd have alpha up here, and gamma there, and we'd have, for instance, so we have Y going into alpha, and alpha going into X, and X going into gamma, and gamma going into Y. Okay? So that's how we get a quiver associated with this triangulation. But again, if we only care about the unfrozen variables, it's just X goes to 1. Right? So this is an example of that algebra that I told you. If you kept mutating, you'll go on forever. And now we see a reason why you're going on forever. It's because you're getting these arcs that can wind around more and more and more. So, and now, again, the sort of general beautiful surfaces. The quiver mutation is exactly the same as the quadrilateral flip rule. Okay, so just like we saw for the case of surfaces. Okay, any questions about this?
So Nima, so even for the higher, I mean, if you had the loop binding around twice, so you'll have, I guess, 3 arrows. Even there, the quiver mutation is still the same rule. It's a flip rule. It's always
the quiver rotation is a flip rule. And notice that if we actually did another, so you were talking about, let's say, so this is already a fun opportunity to draw some other triangulations. So let's start from this triangulation, okay? And now there's kind of an obvious point. I could take this picture and I could imagine like winding the inside loop, right? Let me like wind it around like one full turn, for example.
Yes.
Okay. If I do that, I'm still going to get a triangulation. In fact, that's the kind of the symmetry of the surface. That's the mapping class group of the surface, is to take this internal annulus and wind it around. But you know, if you wanted to draw it, it gets a little trickier to draw, but that's fine. So we take this internal guy. I'm going to wind him around once, but then I can wind this guy around twice, like that.
Yes.
Okay. So that is a new triangulation, and in fact, this has just the same quiver. Okay. Yeah. So so all the quivers are just 2 arrows. That's kind of obvious just from the mutation rule, because if you mutate this, all that ever happens is you reverse the sign of the arrows, right? So all we ever do is go from one to the other
Mm-hmm.
Okay. So but this, again, this is already some very early indication of what the issue is that somehow there's basically one topology here for what the triangulation looks like. There's really one triangulation, okay? But we're representing them. There's zillions of different, so that's what we're seeing. There's basically 1 or 2, depending on whether you label. Anyway, there's one quiver, but infinitely many cluster variants. Okay, so that's the challenge that we're going to have to deal with.
Yeah.
Okay, now guys, I think this, if we are going to have another session, I mean, I don't. How are you all doing? I think I think I should not. I can maybe speak for another 20 minutes to talk about how to deal with punctures, and then I think that would be a natural place to stop. And then if we do another session, I will begin with talking about how to think about G-vectors for general cluster algebras before going into clusterhedron story, because they're very naturally connected to each other. So shall we do that, or do you want to just call it a day now?
No, I think you can do the puncture and then.
All right, let's talk about the.
Yeah.
Because this is an important and slightly tricky point. But it's not all that tricky. But I want to. Yeah. Okay. So let's just do that, and then we'll have defined everything for the surface cases, and the rest is things to ease analysis. Okay.
Okay.
All right. Good. So our topic is punctures and this funny phenomenon of so-called tagging. Okay, so something funny happens, something slightly funny happens if the surface has punctures. Let me illustrate it with the simplest example. So the simplest example is just one puncture inside, and let me say 2 points on the outside. So this would be like bubble diagrams at one loop. Okay, so let me call this A and B, and this arc here, alpha and beta. All right, so let's first look at what the triangulation is here. Well, here it's sort of obvious. I don't need to do anything fancy. I have this triangle, and I have this triangle. Okay, so what the quiver is here is alpha A, beta B. Notice that the green arrows cancel between A and B. So all I'm left with is arrows around the outside like this. In particular, if I only focus on the unfrozen guys, they're not connected at all. So this looks like it wants to be the A1 cross A1 algebra. One. So okay. Good. Okay. So so far so good. This is a healthy triangulation. No problem at all. But now let's ask what happens. Now let's ask what happens when I mutate at B. Okay. So let me actually keep the. I just erased it. I'm sorry. Let me keep the quiver here. Alpha A, beta B, and our picture looked like alpha. Look like that. Okay, so let's mutate at B, and first let's look at it from the perspective of the triangulation. Okay, so what should happen? What should happen when we mutate at B? Well, that means I'm going to get rid of B, and I'm going to replace it with another arc that's compatible with A. Okay, so so who is that? Well, the only one appears to be this one. Let me call this guy B prime after mutation. Okay. Let's see also what it should mutate to on the side of the quiver. So on the side of the quiver, I should have A, alpha, beta. So I reversed all the arrows into B, but I should add something between beta and alpha. So this is B prime, and then here hasn't anything changed. So this is what I should get. This is what I want to get. Okay. Okay. So now we have a number of problems here. So first, let's first look at the quiver. From the side of the quiver, the new quiver that we get, we see that alpha.
Nima, I have a question about this. So since you've drawn one arrow between beta to alpha, but there's also but there are two paths. So shouldn't there be two arrows there?
No, you mean on the right hand side. Sorry, let me be clear, because the whole issue is that there's some problem in following the rules. Okay, So on this side, I'm just applying the quiver mutation rules. Okay. So if I apply the quiver mutation rules on B, I'm just supposed to reverse the arrows, and then since I went from beta to alpha, I'm
Oh yeah. Sorry, yeah.
so that's what I get from the right-hand side. The whole problem is that it doesn't match what I get on the left. There's some problem on the left. Okay, so let's look on the left, and we have many problems. One of them is that if I look at this quiver, we see that alpha should connect to A, right? But how the heck can alpha connect to A here? B prime is blocking any way of drawing anything that I would want to draw between alpha and A. Okay, so that's one problem. A worse problem is that, let's say we now want to mutate at A, right? We mutated at B to get B prime. Now we want to mutate at A. Well, there's nothing we can do, right? If I delete A, who can I draw which is compatible with B prime? Nobody, right? I can't draw this. I can't draw, I can't draw anything. I can't draw this. It intersects B prime. None of these guys mean anything because they're all homotopic to one arc or another. Okay, so we have a basic problem that both the quiver doesn't make sense and we don't know how to mutate further. Okay, so and of course you also see that there's also something funny at the level of the triangle. This is what you can call a self-folded triangle, right? So the one that we drew, this one, if this was going to be part of a triangulation, this is a really quite peculiar triangulation indeed, right? This guy, it's like a triangle that's sort of folded on itself. So there's a variety of difficulties here. Okay, so let me tell you what the solution is to the difficulties, and then I'll give you some intuition. In a moment, I'll give you some intuition for it. In fact, this intuition is going to be closely related to what makes the story of the to one aspect of what makes the story of the clusterhedron later makes sense. Okay, so but let me just say that this is the solution. So the solution is to introduce a notion of tagging on arcs. In other words, for any arc anywhere, inside, outside, anywhere, but it has two endpoints, whether they're punctures or boundaries or whatever. We're going to allow, with some extra rules that I will mention, we're going to allow to have an extra decoration on one end. So it's called tagging. So you might imagine that you draw this little tag on one end or the other end. Okay, so for any given arc that connects 2 points in principle, without saying anything else, we could have a total of 4 decorations for it. Untagged on both ends, tagged on one end, and tagged on the other end, tagged at both ends. Okay, so just bear with me for a second, and I'll give some intuition for what this means. So but there are a few rules. So one, so we're going to have arcs. We're going to allow tags on the arcs, and basically what we're going to do is so tagging rules or tagged arc rules. The tagged arc rules are: 1, we never have just the thing that we got confused about. So we never have any loop that goes around a single puncture and ends at a boundary component, okay? Or for that matter, anything that goes around, that starts at a puncture and goes around a single component. So here it's just that that we have a single component inside, just one puncture, okay? Nothing with just one puncture inside. So these are, we never allow those. Okay. Instead, we allow tagged arcs. And there's a some extra rules, and I'll give you the intuition for it so you can remember where this, why this is happening and where it comes from. We are never tagged at a boundary. So if you have something like this on a boundary, here it's never tagged. Okay, so we don't, this thing is not allowed. Okay. And if we have something connecting two punctures, any of the 4 taggings are allowed. Okay. And finally, we have the rule that if we have a loop ending on a puncture and encircling anything else, it has to encircle more than one puncture, but who knows what else it has inside? It doesn't matter. The loop ending on a puncture has to be either both tagged or both untagged at the puncture. So I can have this guy with no tags, and I can have this guy with both tags, but I can't have one tagged and the other untagged. Okay, so that gives you a new notion of the arcs that I'm allowed to draw on the surface. Okay, I'm never allowed to draw these arcs, these funny, confusing arcs. I'm never going to draw. Okay, instead I'm going to draw. I mean, their presence is going to be better reflected by these tagged arcs. Okay, so I'm going to allow tagging on the arcs, but I never can see it tagging at the boundary. In the situation where there is an arc that goes around a puncture and comes back to itself, a loop at a puncture, they both have to be tagged or untagged at the puncture. And now I have to do a rule for tagged triangulations. So I just have to give you a notion of compatibility. Okay, so let's say I have 2 arcs. So I want to give you compatibility between arcs alpha and beta that might be tagged. So alpha and beta are compatible if you remove the tagging. So let me call that alpha naught and beta naught. If they are compatible. Okay, so basically, I still can't have any chords that intersect or anything. If I forgot about the tagging, they should be compatible. But it's possible that they're compatible because they're identical. Okay, so if alpha naught equals beta naught, then they have to be tagged the same on at least one end. Now the rules look a little bit funny. So in other words, these are identical arcs, alpha naught and beta naught, but if they end, if they're identical, they just have to be tagged the same on at least one end. And finally, 3, if they're different, if alpha naught is not beta naught, and if they're ending on a puncture, there's puncture P and here is alpha naught, beta naught, alpha and beta have to be tagged the same at P. Okay, so those are the rules. And now let's look at how these rules now work with the same example. Okay, so if I have this example where I begin here, 1, 2, with the puncture here. Okay, now I want to do the same thing. I want to mutate on B. Now, when I mutate on B, I used to want to do this, right? I used to want to do this, but I'm not allowed to do that anymore. Okay, so that is now illegal because I'm not allowed to draw this arc. Instead, what I should do is ask, okay, what else can I do which is compatible with everything? Okay, and well, what I can do, what is compatible with arc 1? What's compatible with arc 1 is another arc from 1 to the puncture, but which is tagged at this end. Okay, so this satisfies all those previous rules. Okay, so this satisfies that in this case, alpha naught. So I have two guys that without the tagging are identical. With the tagging, they have to be tagged the same on at least one end, while they're tagged the same at the boundary because they're not tagged there at all. And okay, so then everything is fine. Okay, so so in fact, if I look at all the sort of mutations I can get from this picture. So I can mutate on, let me draw it down here. I can mutate on B, and then I would get what we just drew, where this is tagged and untagged. I can mutate on A. And I'd get the other guy. Be sort of tagged here. And now what happens if I keep going? So let's say down here, I just mutated on B and I got this tagged guy. So what happens when I mutate on A now? So this is A and let's say B prime. What happens if I mutate on A? Well, I get, now I have to delete A, and the only way I can make it work, so now I have this guy, which is tagged here. So now I get to add this variable back. But remember, the other rule is that alpha naught, if alpha naught is not beta naught, then, and they meet at a puncture, they have to be tagged the same there, okay? So that means that, that now I want to draw this line back, but I can only draw it with a tagging there, okay? And so you see, that's, of course, also exactly what we get if I mutate here. So if I here I mutate on B, and then I mutate on A, versus if I mutate on A and then I mutate on B, then I come back and I make this closed picture. Okay, so this is indeed exactly what you'd expect for the A1 cross A1 algebra, right? Because we just have two things interchanging, and so we get a consistent notion of mutation if we don't draw these self-folded triangles, but we read off the but we work with these tagged triangulations instead. Now, finally, how do we read off the quiver from the triangulation? Okay, so so how do we get the quiver from the triangulation? So the answer is that we do exactly what we did before. We ignore the tags. We ignore tags, except for the cases where alpha naught equals beta naught, right? In other words, these are cases where we have two arcs. Let's say going between A and B. There might be punctures or boundaries. I don't know. But they have to be tagged the same on one end, and they have to be different on one end because we can't have identical arcs. So I can't have something like this, right? Maybe I didn't say that before explicitly, but all the arcs have to be different with the tags. So that means that on this end they'll be tagged the same, maybe both tagged or untagged. It doesn't matter. On this end, one will be tagged and the other one won't. So if you see that in the triangulation, for the purpose of getting the quiver, we will replace this with what we naively thought to begin with. We'll replace it with that loop, A to B. Okay. And so you see there's an asymmetry between A and B, because on two sides they have to be the tag the same, on one side they're different. So that tells you who is the origin of this loop and who is being looped around. Okay, so you draw that, and then you triangulate the rest. You triangulate the rest, but what you do is, we have two variables here. We have two variables associated with these two lines. So in order to get the part of the quiver that involves those two variables, I take x and x tagged. So if this is x tagged and x, I take x and x tagged and I put them as two nodes on that boundary of the triangle, and then I draw all the triangles in exactly the way that we did before. Okay, so let me show how this works in a concrete example. So let's say I want to find what is the triangulation associated with this guy. Okay, so 1, 2. Okay, so I want to find the quiver associated with this guy. Well, okay, let me label again. Here's alpha, beta, so here I have my variables. There's some variables here, x and x tagged, let's say. So what I'm supposed to do is look at this and say, okay, in here I didn't have anything else going on, so I just have this. I just have this configuration. So for the purposes of getting the triangulation, I will draw this instead. Okay. Okay, and now there's just one. So now there's just sort of one triangle in this picture. I have so if this is 1, sorry, if this is 1 and 2, I have the obvious and alpha and beta. Then I have the obvious triangle. Alpha, beta. So here's the point 1, 1, 1, and 2. Okay. But on this loop now, so I don't know what, maybe we should call this loop here gamma. So here's the loop gamma from 1 to 1. And so what I do is the same as rules before. I put something on the inside of the alpha line. It's frozen, so it's like that. But on the gamma, I put 2 x and x transpose, x and x tagged, and I just draw exactly what we did before for each one of them. Okay, so I draw that oriented triangle and that oriented triangle exactly the same way. Okay, and so if I look at what I get from that, it's exactly this. So sorry, let me draw it a little more nicely. So we have 1, 1, 2. The alpha, beta, and I have these 2 x's here. So x and x tagged, and so I would have that guy, and if I look at what that looks like in terms of the quiver, I have exactly x I have exactly here x and x transpose and alpha and beta, and I have oh, sorry, you know what I was screwing up. Yeah, so so we draw the triangle and we sort of treat an X and X transpose like they're sort of, we treat them symmetrically. We don't add an extra arrow between beta and alpha. It's as if X and X transpose are just sort of one blob, but that when this arrow goes to this blob, the arrow touches both X. There's a separate arrow from X and X transpose, and when it goes out here, there's a separate arrow from X to beta and X transpose to beta, but there's nothing extra between beta and alpha. Sorry, that's what I was throwing up. So then we get this quiver, and then alpha goes to X, X goes to beta, alpha goes to X transpose, X tag goes to beta. Okay, so that's how we can draw a we can associate a quiver with one of the tag triangulations, and you'll notice that this is exactly the quiver that we wanted. Okay, so that's exactly this quiver that we wanted to get after we did the mutation. Exactly the quiver that we didn't quite know how to associate with this picture, but now we get from the rule that I just described. Okay, so that's the extra decoration which is needed when we deal with punctures. And let me just end with just a few minutes with a motivation for tagging. Okay, so motivation for tagging. And we're going to be seeing a lot more about this general idea, but I'll just be sort of a little bit impressionistic. Well, the idea is that let's say you have a puncture inside the surface. You have a puncture inside the surface. It's sort of reasonable to think that maybe you could have sort of blown this up into a little boundary component. Okay, so maybe I can blow it up with a boundary component with just sort of one point on the inside. I forgot to say this in general, that you're never, in this story, you're never allowed to have boundary components with no marked points on them. And again, that's good for the connection with physics, because all the boundary components are supposed to correspond to some trace factor. So we need to put something inside the trace. So you have to have somebody on the marked component always. Okay? So let's see what would happen if we tried to imagine, instead of having a puncture, we sort of blew it up to a boundary component with one. And now, really, doing this is adding one variable to our whole story. We have this one extra node. We're going up in dimension by one. But we also get something else that we get to talk about now. This curve that wraps around this little annulus there was not present in the case of the puncture. See, the puncture is really an infinitely small hole, and we can sort of shrink this delta down to be arbitrarily tiny and get rid of it. But after we blow it up in this way, we have this interesting loop that runs around this hole. Now, it's intuitively, I should be able to intuitively, for example, if I took the picture of all the G vectors, or somehow, let me say it intuitively, we should be able to project. We have to lose one dimension. If we want to map things in the right-hand picture to the left-hand picture, we want to be able to project in some direction to go from one higher dimension to lower. So intuitively, we should project through delta to go from the right to the left picture. But now you see we have an issue. Because once we have this delta, let's say I have some, whatever it is. So let's say I have some arc, let's say I had some arc that touches the puncture. The question is now when I blow it up, what does it go to? And you see, it now can go to infinitely many things. It can go to this, it can go to this, it can go to this where it winds around any amount in this direction, but it can also wind around any amount in the opposite direction. Okay? And so we have something slightly funny that once we decide to blow up this puncture, maybe slightly regulate it to something which actually has an annulus with a point inside. Now we have two kinds of arc in the right-hand picture that that descend to an arc ending on a puncture on the left. And we get to decide whether something is winding around a lot in the positive direction or the negative direction. Now, as we'll see later, all of these, for example, all the G vectors related to the guys that are winding positively, they're all related by adding delta. And the guys that are winding negatively are also related by adding delta. But I can't go all the way from minus to plus. So there's kind of a plus winding sector and the minus winding sector. And they're all just related by adding delta. So after I project through delta, they all end up on the same vector downstairs, but I get a different vector for positive and negative winding. And so that's why we need tagging. Tagging is keeping track of whether, in this way of regulating the story, when we add this, when we blow up the puncture into this little annulus, whether the variables that ended on the puncture were winding around clockwise or winding around counterclockwise. That's the sort of beginning of the story. And then we'll be thinking a lot more about what these surfaces with the annuli inside look like. All the rules we saw for tagging before really descend from compatibility and projection through delta in this picture where we blow up the punctures into little annuli with marked points. Okay. All right. So I think that's it. You guys are heroic for staying up so late, but I think what I told you about cluster algebras in general are most of the general things you need to know. And we've gone through essentially all the non-trivial details of thinking about triangulation and also tagging for surfaces with punctures. And so the next session, if we end up having it, I will start with a final useful thing, which is how you can just read off G vectors from a picture of a a choice of initial cluster. I can read off G vectors for surface cluster algebras. A choice of initial cluster is just some particular triangulation. And if I take any old other arc that I want to draw this other arc. I draw the triangulation, draw this other arc, and figure out just how to read off the G vector without doing any work. And there's, without doing any hard work. And there's a very beautiful picture for how to read off the G vectors in general for surface cluster algebra. So I'll begin by reviewing that, and then we'll return to the physics problem of defining these cluster features. All right, guys, that is it. Are there any questions for those of you who are awake?
Any questions?
I can't believe
Just a
17
quick
of you
one.
are still wide awake. That's impressive. Yeah.
The X and X transpose, these are the exact the additional points in your kinematic space in that the causal diamond kind of picture.
Yes, very, very much so. Yes, absolutely. Yes. So thanks for asking that. Let me actually go back and see if I can explain that. Yeah. So yes. So if I now go all the way back, let's talk about yeah, great. Let's talk about the D4. And so Dn is just triangulations with one of a surface with one puncture. Okay. So let's say we're doing D4. So now we have this puncture on the inside, and again, the kind of garden variety triangulations are like this one. Okay. So actually, this is a nice exercise. Let's do this guy, and let's look at what the sort of dual Feynman diagrams are. Okay. So, all right. So that's just a box. Now let's just do some mutations. For example, let's mutate on let's mutate on this line. Okay. So still nothing funny is going on. Now I'm doing this exercise so that you see that this tagging business is all about tadpole diagrams. And it's sort of forced on you by thinking about tadpoles and how we interpret them. So let's keep going. So the first thing I do is so I'm going to get rid of this blue line and who can I add instead? So let's just, so I can add this guy, okay? And so who is this at the level of the, so what have I done there? So let me not keep drawing the dual. So this guy is, I've done the kind of ST channel flip on that diagram. So this now is turned into a triangle like this. Okay? So far so good? Okay,
yeah.
And now let's do something else. Now let us, yeah, we're still not there. So let's mutate, I don't know, this guy. Okay. If I mutate that guy, then I can replace him with this one. So this one's still okay. And that one is, let's see, who did I get rid of there? That one is the ST flip on this line. So this is already something slightly more funny. This is like a, something like this. I put a bubble on an external leg, okay? And now I start coming into trouble, right? Because now what happens when I, let's say, mutate that guy, then okay, if I did it most naively, then that's the same situation we had before, right? If I did this most naively, I would have to draw something like this. And what does that correspond to in our Feynman diagram picture? It's like getting rid of that propagator. So, you know, I had this bubble, but I'm going to get rid of this propagator and blow it up in the other way, and I get a tadpole, right? So what I'll be left with is something that looks like that. So far, so good?
Right.
Okay, so now you see, purely at the level of the diagrams, things look okay. I mean, the triangulation is a little funny, but that's but okay, it's fine. Let me draw it a little more nicely again. And you see there's also an, okay, so let me draw it again here. So, I have that, right? And I still have this guy, right? So this kind of looks okay. Like this variable that I got is like that propagator, right? That new tadpole propagator I didn't have before. Whereas this variable is like that loop variable here on this. Okay? So this is perfectly sort of sensible looking, but you see we have problems with continuing to mutate. We have exactly the same problem as before. You know, now I have this tadpole. What am I supposed to do with it? I don't know how to mutate any. I don't know how to do any more sort of ST there's no obvious ST mutation flip that I can do on this guy. Okay.
Right.
So I mean, who can I do? I can mutate it back, but it doesn't seem like there's any ST flip that I can do here. Okay. So here's the sort of problem at the diagram side. If you gave me that guy and you told me mutate now this guy, which is what we're talking about, right? We want to mutate this and we don't know where that's supposed to go. Well, similarly here, there's no ST flip that I can do on that guy. So there's not obviously any place for it to go. Okay?
Right.
So what we do is double everything. So we're doubling everything by saying that in fact there's two kinds of propagators, the Y and the Y tilde. And here they correspond to tagged and untagged. And that also means that this tadpole propagator and the loop propagator are then treated on a sort of more symmetrical footing. And you can, so one is tagged and the other one's untagged, okay?
I see.
At this point, what we do instead of drawing this with the legal tagged and untagged, with the legal tag triangulations, it's exactly what we talked about. Okay, exactly this. And that's and now I have this guy and I have something tagged. I'm still perfectly free to identify this with that Feynman diagram if I want. But now what happens when I mutate? Happens when I mutate this guy. When I mutate that guy, I can go back to this. Sorry, I can go back to this. But now this has to be tagged. Okay, so in other words, I'm saying that when I mutate on the green, I go back to a bubble diagram. I go back to a bubble. But now there's this second kind of loop. Now I have the sort of tagged kind of loop there. Okay? And now if I keep mutating, I'm eventually gonna, well, I'll go back to the triangle, but now that's gonna be the tagged loop for the triangle. Okay, so that's sort of what has happened. And eventually I will get to the tagged version of the box. Okay, so I will see the tagged version of everything that I saw before. So somehow the price here. So let's think about what we're doing. I maybe should have said this at the general point to begin with. There's something quite remarkable in this whole story again, which is we normally think that we draw all Feynman diagrams together, but there's no sense that one diagram is related to another diagram. Nothing. They're all separate things. We're supposed to add them all up together. On the other hand, for example, the projectivity of the form tells you that somehow the diagrams are related to each other. There are close ones and far ones. The idea that we can put them on the vertices of a polytope also tells us they have somehow relationships to each other. So, but if we want to see those relationships, it's very remarkable that you can start just from one diagram at tree level, at one diagram, and do ST flips and get all of them together. Okay, so that's quite a beautiful thing. So if you want to keep going with that idea, that we start from any one diagram and we can reach all the other ones by a sequence of these ST flips, then you get stuck. Okay, then you get stuck, and the only way to proceed with that idea is to introduce these sort of two kinds of variables. Okay, and so but then once we do, then it's possible to get from any one of them to any other one by the sequence of these generalized ST flips, where the generalization just means that when you get to this situation where you have a tadpole, so the whole thing is really sitting there in this example already, right? When you have this situation where you have an x and a y, it's not obvious what I'm allowed to do to y, but our rule is that we just define this can mutate back to x and y tag. This is x tagged and y. We can go back to something like that. Okay, so yeah, and so then once we do that, we can then go back to this picture that I showed you for dn. Oh, sorry, I didn't wherever it was. Yeah, here. And indeed, so that's exactly what these two variables at the two ends of the dn of the dn quiver look like, and once you do that, every single vertex of this polytope is associated with ordinary Feynman diagrams, and this is all of them there are. But we are allowed. You see here, here it's labeled by y and y tilde. So one of them is the propagator for the tadpole. Sorry, it's so small. The other one is the propagator for the.
Okay.
Answer your question?
Yes.
Yeah, and it's and it is a little bit peculiar. And actually, in this particular case of dn tilde, it turns out there's something very pretty. That if you look at this whole polytope, there's actually a symmetry that interchanges the y and the y tilde variables. And you can and if you then just chop the polytope in half, if you literally chop it in half along this symmetry plane, you go from this real polytope to what we call the sort of dn bar polytope, where you chop it in half. Once you chop it in half, you're only keeping one copy of all of the loop variables. You're adding a face, but quite beautifully, that face is the face on which you see all of the tadpole diagrams. So this is a little extension of the story that you can sometimes chop these things in half and keep just one copy of all the variables you want. But in a sense, but this looks like it's maybe, at the moment anyway, it looks like it might be a low loop accident. This issue that there's many copies of the variables we want is the heart of the difficulty of going to 2 loops and higher. And we're really gonna have to think about it in a different way. And that's what we'll talk about next time. I should say, in practice, in this example, there's nothing wrong. After you get the form, if you like, you can just shove y equals y tilde, and that gives you the answer. I mean, so there's no difficulty, but somehow to see the whole structure and to see the polytopal structure, you need to do this doubling.
Okay, thanks.
So Nima, at the tree level, there was this, in your previous paper, there was a color is geometrized. You know, you went to the big kinematic space and there was a 7-term identity that you used to show.
Yes.
So is there something similar that you could do now at the?
Great question. I would, I've not thought about it, but it would be wonderful if there is. That would be really great. Yeah, I've not thought about it much. There are some reasons to expect that it should be possible. But no, I've not thought about it. I mean, I've not thought about it in much more than the words that I just said. Yeah, that would be extremely cool if we could see. Yeah.
Right.
Yes.
Right. And the other thing was that there were also in that same paper you had the permutohedra for some of the non-planar channels, right? For in the kinematic space, you had the permutohedron.
Oh no, that wasn't. I mean, that was some later papers by Song and friends. That's right. Yes, that's right. Yeah. So I mean, well, you know about these things more than I do at this point. But there are various. Well, there are various generalizations. There are classes of like graph associahedra, which are naturally Minkowski sums. There are other kinds that there are things that are relatives of cluster algebras.
Right.
So I presume that I presume that to the extent that there seems to be such a lovely connection between the ordinary sociohedron and these other algebras that you've written about these other structures, I assume that we'll see something like that for these other cases too. But I don't know yet.
I mean, I was thinking that if you take the forward limit of n+2 permutohedra channels, then one should be able to generate some non-planar one-loop integrants.
Oh, sure. Yes. I certainly agree with that. Yeah, and in fact, yeah. I mean, this is kind of yeah, absolutely. This is a basic point. When you have 2 loops even, but even more so at multi-loops, there's no ordering between the loops. So once we sit on cuts involving the loop variables, we're exposing lots of sort of non-planar structures at the level of tree-like things. Yes. Precisely because the ordering is gone once we have many loops.
Right.
So
right.
yeah, so non-planar things in that sense are sitting there inside cuts of planar multi-loop amplitude. Absolutely. So what I hope you guys have seen from this, I mean, those of you who haven't seen this thing before, is that this sort of cluster structure is a very basic thing that's associated with surfaces. I mean, I've just given you some definitions, but this thing that we saw in the simple intuitive examples, that all the triangulations of a surface are actually associated with are associated with a polytope. That's a remarkable fact. That's a remarkable fact that actually implies that if you take all of the cones associated with the normal vectors of this polytope, that they tile all of space. So we have these sort of two very closely related facts. There's this kinematic space picture for these polytopes. There's the fact that the normals of the polytopes tile all of space. And this is something which is this is something that's just associated with just triangulating a surface. Now that and in this particular case of the surfaces and these little extensions with one puncture where we get finite type algebras, everything is equivalent to everything else. There's really something, there's something interesting and new to try to understand for the general surfaces. And to begin with, the parts of the story that we know port are that there are these cones, and the cones tile, and they don't leave any holes, and they tile space, although they leave some sort of low codimension regions untouched. But just that alone is enough to guarantee that there is a form that's projective, and a subspace where you pull it back, you get the amplitude. Okay, so already that basic fact at the level of form is reflecting a sort of deep, not obvious fact about the structure of surfaces. And again, it's a not obvious fact that's not in your string theory textbooks, even though we're supposed to know everything about Riemann surfaces to think about a string theory at loop level. It's a new fact about surfaces. It's an interesting new fact about surfaces. And it's fascinating that this interesting new fact about surfaces is somehow connected to these new ways of thinking about amplitudes in terms of canonical forms for positive geometries. But because this is not completed mathematics, I'm not yet telling you a totally uniform story. In the story of the associahedron in kinematic space, I could just begin and say, oh, we're just going to look at this kinematic space, look how nice it is, these causal diamonds, wave equation, poof, 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 everything comes out. And now we're sort of, again, it's a little bit more experimental, but we do have something to guide us. We know that something about these G vectors works magically. And so we're going to take that as an inspiration and then run with the story and see how we deal with this funny infinity. And then in many examples, two loops, non-planar, lots of interesting examples already, we can actually tell an analog of the story in kinematic space. So we can just begin with the kinematic space, talk about some analog of the wave equation. Now there's going to be different regions of the kinematic space, and so we have to sort of talk about how we might want to attach them to each other. Then if we just talk about all the ordinary Feynman diagrams and all the ordinary arcs, we'll find that there are sort of disconnected pieces that cannot talk to each other. We need some universal guy to talk to all of them. And that universal guy that talks to all of them is sitting there in the surface. It's exactly the sort of delta variable that winds around the interior boundary components. But once we see that, there's a natural way to stitch the various parts of the kinematic space and the associated wave equations together and get some beautiful clusterhedron polytope. So they're analogs of these pictures, but I think we still don't know. I mean, we still don't know completely ab initio how you would how you just stare at the kinematic space and write something down. You have to stare at it and see it as different components and try to glue them together in interesting ways. So that's why. So I'm saying all this to sort of justify why I spent so long talking about the cluster algebra part. For the finite type cases, 3 to 1 loop, I could, even though the cluster algebra is very useful and it's behind it, I could just tell you the story in kinematic space, and it's very nice, and you could just we could just call it a day. But at our present state of understanding, as we try to push it to all loop order, somehow the cluster structure is a huge guiding light that tells us something good is guaranteed to happen. Even before we find the full convex realization for all of the possible cases and so on, the full ABHY-like realizations. But it's conceivable when all is said and done that there will be some sort of master way of understanding everything from the perspective of some large ABHY-like realization, and then we'll be able to read back out all these remarkable phenomenon about the G vector cones, tiling space, and so on and so forth. So anyway, so we don't yet know which one of these perspectives is going to be the most useful. So that's why I'm sort of trying to proceed to describe things on both tracks. Anyway, that's an excuse for why it's taking me so long.
but sir, it already You've gone beyond the CHY, right? Because CHY, I think only up to 2 loops people have been able to write the integrand, right, in the CHY world. I mean, not gone beyond, as far as I understand. Through this, even through this ambi-twistor string, they have only gone up to 2
Yeah,
loops.
I don't know. I don't actually remember. I know that there's some stories there at 2 loops. Yeah.
Only,
yeah, so
only,
they're,
yeah, only up to 2 loops. Like, but the clusterhedra story is like going beyond, right? So in some sense.
yeah, I mean, of course, we think that there's a clusterhedron to all loop order and to all orders in 1/n. Okay.
Yes. Yes.
So it's not even just the
Yes,
planar.
yes.
So and yeah, and so what I will talk about in detail are first double trace at 1 loop, which is so double trace at 1 loop are these double trace at 1 loop are I don't know if you can see, yeah. But double trace at 1 loop are things like this, would correspond to these triangulations. So I haven't seen anyone talk about double trace 1 loop things. Then 2 loops is just triangulations here. So these we understand completely. Okay, so and by the way, this double trace at 1 loop is also a class of cuts of the integrand to all loop order. In other words, if I have, let's say I have 3 loops, okay? Let's say I have 3 loops, then I can actually have a cut where I demand that the 3 loops are attached to each other in that way. And then on that cut, it's exactly the same. See, this is the special case of what we just talked about before. On that cut, it is the same as having an annulus inside with 3 marked points on it. So in the planar 3-loop amplitude, there's a cut of the amplitude that gives me this non-planar information of this double trace 1 loop. Okay, so we have that under control. We have the 2 punctures under control. We have things like a torus with the once punctured torus under control. Those are just like vacuum diagrams, but vacuum 1/n leading 1/n corrections, 2-loop vacuum diagrams. So yeah, that's where we are up to this point. But when I say that's where we are, I mean oh, sorry, we're also in the middle of I think we're basically understanding already this 2-loop double trace. Okay, so that would be diagrams like this. Okay, so that would be surfaces like this. Mm-hmm. So what begins to happen at what actually already begins to happen in the once punctured torus, and also for the 3 punctures, is just that as I mentioned, the whole story is about learning how to deal with these variables. These kind of variables are not part of the usual cluster variables, but they play a crucial part in making the story make sense. And all the examples that I talked about so far, there's a finite number of them. Like there's 1 such variable here in the 2-loop case. In the 2-loop case, there's also effectively just 1 such variable. And in this 2-loop non-planar case, there are 3 such variables. So when there's a finitely many such variables, we have a pretty clear picture for what to do. And then something new happens at 3 loops and higher, and also for the once punctured torus. To begin, that's the first case where it appears when you start having an infinitely many of these variables too. And so anyway, that's what we're trying to. That's what we're now trying to understand. But as you'll see, there's a sort of common strategy. It's not like something totally new. It's just we have to see whether the strategy keeps working in all these cases. But I think there's a uniform picture for how it should work in all the cases. And I should also say that there's something remarkably gravitational about these variables. You'll see what I mean when we talk about it. But there's a sense in which they're kind of some objects that are universally coupled to all the other particles. Something that we didn't want, but which is sort of forced on us for these pictures to make sense. And so what we're getting naturally is the amplitudes for our biadjoint phi cube theory coupled to this other sector of stuff involving these delta variables. And there's a notion of a weak coupling that we can choose to dial down the amount by which this stuff interacts with the things that we started off with. But we're also in the middle of trying to understand whether this is more than an analogy. I mean, whether there's really a sense in which these deltas are giving us gravity. Because it's striking that it arises in exactly the same place that it arises in string theory for the first time in the annulus diagram. We know that we get closed strings inevitably, even if we didn't want them, in the double trace pieces of the open string scattering. So that's exactly where we see this funny new stuff making an appearance as well. And there's various senses in which there are some strong analogies between this extra stuff and gravity, but we want to see if it's more than an analogy. We can really think of these as some kind of gravitational sector coupled to stuff that we want. But that's still speculative. Yeah. But indeed, one would have to see how much of all of the story goes through. We have to see whether we can still find these binary geometries associated with these spaces or not. Are there U variables associated with them or not? Are there anyway? There are a lot of open questions to see whether we can define the analog of these stringy canonical forms for them. I mean, so whether we can find the kind of cousins for phi to the 4 and phi to the p theories in the way that you guys have been looking at. I don't know any of those things. I would just like to get this story. This is a kind of a pretty well posed problem now, and I think if we completely nail it, it'll be progress.
Yeah. Any other questions? So let's unmute everyone and thank Nima once again for.
All right.
Yeah.
Thanks, guys.
Thank you, Nima. Yeah. See you tomorrow.
Yeah, definitely. Thanks a lot.
Thanks everyone for staying back.
Yeah, I'm really impressed, everyone. I'm really super impressed. All right. See you later.
Bye, guys.